PVT in Whitson Plus, what you'll see is that we'll go through a lot of PVT theory and then show you how you can utilize that in practice and how it's relevant for you. One thing that's worth mentioning, if you, I see probably some of you have actually done this class before. So these are a part of courses that we run every single year, and that you as a Whitson subscriber or the company you work for has access to. And you can find all of those courses if you go to whitson.com/training. So if I was in a browser here and I go to whitson.com/training, you'll see all our public courses, all the software courses here related to Whitson Plus, et cetera, et cetera. So that's the first one of this. And this is where we dedicate time to only deep dive into a particular feature or set of features in the software. And the first one here is PVT and phase behavior. And why do we do that on Valentine's Day itself? Well, it's because we love PVT, but it's also super important for everything you do as an oil and gas engineer. If you think about it, what we're selling as an operator, that's oil and gas products. And oil and gas products, they're behaving differently at different temperatures and pressures. So you know, when we talk about a stock tank barrel of oil that we're selling, maybe that definition is even different in different countries. So even there, when we're selling the product, PVT becomes relevant. Okay. And that's really the essence of what we're going to talk about today. So a little bit of general information. The first thing is that we're going to try to keep it practical, and we're going to also try to repeat a bunch of stuff. So one thing that's new as of this year is a bunch of case studies that we're going to go through together. And we're going to do a lot of the stuff that you're going to do in Whitson Plus, but we're going to do it in a systematic way for a wide range of fluids in all kinds of unconventional basins. And these are real data sets that I'm going to basically drive, but we're going to together go through how you would probably initialize these wells and how you can actually use the GUR, the producing GUR, as your best friend from now on. If you hopefully we'll learn something from today. So it's a half-day course. It's just from 8 to 12 p.m. We try to keep it interactive. So if you have any questions or any thing that you would like to ask about, feel free to ask about that in the chat window, or just unmute and ask the question. So when you're not talking. We'll send out all the digital material after the class, including the class recording, presentations, etc. And of course, some of the slides, and I'll mention those slides, they're more meant for you later. A bunch of you guys asked if it was fine to print the material and stuff like this, and that's of course totally fine. And you can keep that as a reference for later if you're going to deal with fluid sampling or whatnot. Just one real disclaimer, this is not an advanced PVT course. If you really wanted to know a lot of very advanced topics, we actually have a 5-day course next week for people who really want to deep dive into Whitson Plus, and that's done by Marcus Hayes and Bill All and some of those guys that work day in and day out on PVT laboratory reports, quality checking, equation of state model development, etc.
Hey, Matthias.
Oh, hey, Curtis.
Curtis, just wanted to say hi to everybody. Interrupt you in your full swing. Want to welcome everybody. I'll be in and out through the session, but you're in good hands with Matthias. He's not an RTA guy. His true love is PVT and Lucy. That's it. And so just want to make sure that y'all feel comfortable. If you have complaints, just send them directly to me, and we'll take care of those PVT issues. But hope you enjoy the day. It's going to be a great thing. It's like really PVT, like you said, PVT, practical PVT, but in a complex fluid system like tight unconventionals are. So I want to just wish the best for you. If there's any things that come up, Matthias, that you get, somebody gives you lassos you and you get into trouble, then just make sure that I'm joining and we can have a little discussion on that. But otherwise, I think you're in great hands with both Matthias and the examples and the software. So have a great day.
Excellent. Perfect. So if you have any hard questions, shoot them in the chat, and Curtis will answer them. So so this is great. So we have we have the godfather of PVT with us here today, so that makes it even more fun. In terms of the material that we have the slides with us. We have the access to the software. If you have any issues with the software login, just send it in the chat here or send an email. There will be a break, around I guess 9 a.m. here in Houston. So I'll make sure everybody's logged in and stuff like this. So no, don't stress with it. There was also sent out some preparation material. That preparation material we really recommend you to read, especially if you haven't had that much exposure to PVT before. Great. And I mentioned this already, but just make sure that you have access to Whitson Plus, and don't use like most of you guys have actually access to Whitson Plus through your company. But this is a different domain, so it's dedicated for courses, and there's a field there that we're going to use for the exercises. But there's no usage of that until we get to later in the class. Great. What we're going to try to do when it comes to the logic of how we progress into the course is that we're going to start with the petroleum fluids after we covered some intro. We're going to go further into fluid sampling, lab analysis, understand what a PVT model is, and then primarily utilize that PVT model for engineering value-adding exercises. So this is where we are going to put most of the emphasis of the class today. Some of the course goals. This is a nice slide for you to, after the course, did you actually learn some of these things? So the first thing we're going to learn is to classify a reservoir into black oils, volatile oils, neurocritical fluids, gas condensate, wet gases, and dry gases. We're going to try to understand the difference between in situ and reservoir representative samples. That's a very important differentiation. We would like to conceptually understand what an equation of state is and what the inputs are. We're going to try to predict PVT data or a composition from using readily available data, such as the GOR, a producing GOR, or liquid API gravity, etc., and an equation of state model. We're going to perform fluid initializations on a shale well using readily available data. And this is kind of what most of the day-to-day Whitson Plus users are doing on a well-by-well basis all the time. So that's going to be a big focus of the course. And then we're going to estimate PVT properties from that. We're going to try to use this in some simple calculation exercises where we're going to calculate oil in place and gas in place for different fluid systems, whether those are oil and gas systems or even two-phase saturated systems, and also show you how you automatically can generate the tables and understand the most important parts of a PVT report. So there's a lot of things to cover, but I feel really confident that we can get through most of this today. And whether you have done a lot of our PVT in the past, or if you've done none of it, I'm sure there will be something for all of you to pick up today. And especially if you've never heard or done a lot of PVT in the past, in the preparation material, we sent out a petroleum reservoir fluid properties document. It's 3 pages long, and it was actually something that Curtis wrote in the early 90s for AAPG, which is I think it's for the geologists primarily, but it's covering a wide range of very important definitions, and it's also a very concise and small document that is a very nice intro if you haven't heard anything about PVT before. So it covers all the most important terms. It covers a lot of the most important concepts, discusses even water PVT that we'll get to a little bit. So read that if you haven't done it before, and that's probably relevant even if you've done a lot of PVT in the past, or if you have just heard about it. Maybe this is the first time you hear about it. And if it is the first time you hear about it, and what we're going to talk about PVT as in this course is the review of physical and thermodynamic properties of gas and oil. Commonly done, the phase and volumetric behavior of petroleum reservoir fluids is referred to as PVT, which stands for pressure, volume, and temperature. And a good example of what's called an equation of state is the equation we're seeing to the right here. Can anybody in the chat guess what equation this is? The one to the right? Maybe somebody knows. I'm going to see just if the chat is. Ideal gas law. Exactly. So the equation to the right here is the ideal gas law. And as we'll learn later, that's actually one of the most simple or fundamental equations of state that we've had And a lot of the things we were doing in oil and gas, where we're using more advanced equations of state, they're kind of like just more advanced versions of this fundamental equation. So we'll talk about that later. One other thing that comes up very often, that's also discussed in that document that I sent, is what about water? So for most of what we're going to talk about today, and when we talk about PVT in general, we don't put a lot of emphasis on water because it doesn't exhibit a lot of very complicated PVT. It can be a little bit of gas in solution with water, etc. But primarily for what we are doing in unconventional shale, call it model development and stuff, what's really important is to home in on the salinity. And we'll talk about that also later, because salinity and temperature is what dictates the density and viscosity of the water. And of course, that can be important for bottom hole pressure calculations for once, but it can also be really important for where you have a lot of water being produced. And it can also be important just from, viscosity obviously has an impact on just the regular well performance as well. So that we'll talk a little bit about water. It's one slide exactly, and I'll show you how you can change water properties as well in Whitson Plus consistently, and then that will be how you change it in every single feature essentially. Before we're going to continue, and I see in the chat and stuff, I see there's a little bit of people can't log in and stuff. I'll help to make sure that everybody is able to log in, but we can do that in the break. But before we get started with the fundamental theory and whatnot, it's important to just introduce some vocabulary that I might be using many times throughout the course without even thinking. And that's it's because I've been hanging out with Curtis and our colleagues where we work with PVT every single day. But we also realized that for people working in operating company, maybe working on PVT day in and day out is not the only thing you do. So we want to repeat or at least introduce some basic vocabulary that hopefully is the most advanced new vocabulary for you before we're going to go through the course today. And those items is an equation of state model. It's the word composition. It's the word flash. It's the word K values, a representative sample, and what we call solution CGR, or the vaporized oil ratio. Okay. So these are 6 words that if you've never heard about them before, they can be maybe a little bit confusing, but hopefully at the end of the course, you've heard about them, 2-3 times, such that you're at least a little bit familiar with it. And we've tried to list this in an order that makes sense. So when I'm going to go through it, it's good that you know what an equation of state model is before for instance, what a flash calculation is. So this is just intro, where we're going to talk about these for the first time, and then you'll hear about it at different places throughout the course today as well. So what is an equation of state model? For now, I don't want you to think too much about what's inside of the model. It's obviously a PVT model that we'll talk more about later. But I would like you to focus on the inputs and the outputs. So there's 3 different inputs that can give us some very important output. And that input is pressure and temperature. And pressure and temperature is something we're used to from the kitchen. We might have a pressure cooker in the kitchen. We might have, or we boil water. We know that the water boils at 100 degrees C. So we have a relationship in our day-to-day life with pressure and temperature. And then it's an additional input, which is called a composition. And that's just the amount of different components that makes up a fluid. And if you want to think about this a little bit simplistically, think about that as GOR or CGR. So if your GOR or CGR is changing, then your composition is changing. So to use an equation of state a little bit simply put, you need a pressure and a temperature, and you need call it a GOR or a CGR. And with that input, you can then estimate a wide range of PVT properties. It can be formation volume factors, solution GORs, viscosities, densities, compressibilities, etc., etc. Okay, so that's the end goal, and we also need to know our inputs. So if we have those inputs, we can get to our end goal, which we need for a wide range of different calculations. So as I mentioned, this first word, composition, if you've never heard about it, or maybe you are a chemie by background, then you know this. I was not. I didn't even have chemistry in high school. So I remember when I took Curtis's class, and every time he mentioned the word composition. I was like, I had an intro class in chemistry or something in university, and I was like, okay, I lost the rest of the sentence because it just confused me so much, that word. But it's nothing else than just the amount of different components that we usually express in terms of mole percent. Okay, if we're looking at a total reservoir fluid, we typically use the symbol Zi. If you're looking at the vapor phase, we use the symbol Yi, and if we are talking about a liquid, we're using the symbol Xi. And here the color is not arbitrarily picked. So typically throughout the slides, if you see the color red, we're dealing with a vapor phase, and if you're seeing the color green, you will be dealing with an oil phase. Okay, and that's something you also see in the software. That that's why the oil rates are green and the gas rates are red. That's why the dew points are red and the bubble points are green. So hopefully that can be something that will help you throughout the day today. If you want to think about it in day to day, what is a composition? Well, think about air. Has primarily nitrogen and oxygen. Sparkling water that I drink way too much of has primarily water and a little bit of CO2 and maybe some other stuff as well. And then for a petroleum fluid, for an oil, for instance, it can just be a more complicated version of this. We just have, we might have some of the non-hydrocarbons like CO2, H2S, and nitrogen. We might have some, ton of these heavier ends that it can actually be thousands and thousands of isomers of. So it's just a way more complicated version of the same thing. And that's what we're dealing with when we're dealing with oil and gas. So if you have a composition and you have an equation of state, you're ready to, you can do a so-called flash calculation, where I use the word flash all the time. I say, okay, we took the reservoir fluid and we flashed it to stock tank conditions, or we exposed it to the separated conditions and conducted a flash, or we flashed it to the surface. Use it in many ways that not necessarily means the same thing. The one thing it does not mean is we're not referring to the superhero, or one of my nightmares earlier was Adobe Flash Player. I don't know if that was a thing over here too, but everything that had that was just a nightmare. So there's has nothing to do with that, but it's related to the so-called flash calculation. So that and if you look at it a little bit rigorously, the two-phase isothermal flash calculations that are used in processes where you have vapor liquid equilibrium. That's what you call a VLE process. And probably the most, if I want to, try to connect that to a day-to-day exercise for you all, you produce a fluid, expose that fluid to separated conditions, for instance, and then you're getting, if everything is in equilibrium, you're getting a vapor phase and you're getting a liquid phase that will be, a function of whatever those conditions are. Again, pressure and temperature. And the compositions are input to that, and then you can conduct a flash calculation to see whether will actually separate into a vapor and a liquid at those conditions, or if it will actually remain single phase. And what will dictate what if it remains single phase or go into two phases is whether it's above or below the so-called phase envelope. Okay, so we take a more visual example. If you think about the pressure being reduced in the reservoir, initially we're dealing with, for instance, an undersaturated oil. In this case, this is a near critical undersaturated oil. Everybody have seen probably the phase envelope before. If not, we'll talk about it. So we say that it's undersaturated when it's above the saturation pressure. And then we go down to the so-called bubble point, also called on a general terms for both dew points and bubble points, we call it the saturation pressure. And that's defined as when the first little bubble of gas is coming out of solution. And that composition of that fluid, that's called called the incipient phase. And if we lower the pressure much more in just one stage and didn't remove any fluids, we would then be able to get a gas phase and an oil phase. And the flash calculation will tell us the amount of the different fluids, and it will also tell us the composition of the individual fluids. What dictates that is something called K values, and that's very important for you to understand as we get later in the course. That will help you explain some of the more complicated phenomena and shapes of curves. And many times you can think about an equation of state as a K value generated. And what is a K value? Well, if you want to simply put it in kind of layman's term, is that K values just represents the relative preference of a component to be either in the gas phase or in the oil phase. So if the K value is larger than 1, the relative preference is to be in the gas phase, typical, for methane, etc. So if you look at the plot to the right out of the SB phase behavior monograph that Curtis wrote around 2000, that methane likes to be above the line here in blue, which is 1. And then if you're a very heavy component, let's say you're, here we're dealing with a hexane, for instance, and if hexane is that's a heavier component, and you see that likes to be below 1. So the relative preference is to be in the oil phase. Okay, and that will be different for the different components at different temperatures and pressure. Now, a very, very important practical aspect is this term that we call representative samples. And in this course and how we define what's representative or in situ representative is very important, and it makes a ton of sense. So the first thing is what we define as a reservoir representative sample. That is any uncontaminated fluid sample that's produced from a reservoir. Okay, so if you're producing both above and below the saturation pressure, your GR is changing, doesn't matter as long as it's not contaminated, which is not really a problem for tight unconventional fluids. The second thing is what we define as in situ representative fluid samples. And that is a sample that's a representative of the original fluids in place. And here, a lot of people think that the accuracy of PVT data, when you bring it to the lab, is related to whether the sample is in situ representative or not. And that's not true. And we'll talk much more about that later in the class today, that you can have an awesome PVT report that is recombined at the quote-unquote wrong GOR, and that you can use for a lot of very important engineering, and the data quality is great. And vice versa, you can have a really, really bad PVT report, but the sample was quote-unquote recombined at the right GOR. Maybe there was a lot of material balance issues, etc., in the different PVT experiments. So we'll talk about that, but this is a very, very important thing to grasp. And it's actually your job as an engineer, as we'll get back to once you have a fluid model, be able to in situ or to create a fluid initialization for your reservoir that makes sense. And when you're dealing with a building of a model, like Curtis has done this for 30, 40 years, and what we've done also for every single unconventional basin in North America, which maybe I didn't mention earlier, but if you go to our webpage, you can see that for the Permian, we've taken a lot of PVT data from throughout the play, 200 plus PVT reports, and we've created a so-called PVT model. And those can be both in situ representative samples, and they can be reservoir representative samples. So they can be both. And why would you like to have both in your data set? Well, if you look at how you're producing GORs is changing over time, you will see that you don't want to only have a PVT model that's representative for when time is equal to 0. So in practice, we try to use in situ representative samples together with the properly tuned equation of state to initialize the reservoir model. But this is done after the fact, after you've developed the model, and that's what we're going to do together here. We're going to look through the case studies. So just to systemize this for you a little bit, if you've ever worked conventional reservoirs, where you have maybe mud contamination, etc., this might be something that resonates with you. But then in situ representative sample, that is would be a sample in a very simple terms that's collected at bottom pressures above the saturation pressure. And that sample would also be reservoir representative. If the sample is collected below, while the bottom pressure is below the saturation pressure, and the GOR started to rise, obviously that sample is not in situ representative, but it's still reservoir representative. And the only way to make it not either in situ representative or reservoir representative would be to have some mud contamination. So some components that you bring into the mix that wasn't there originally or naturally in the reservoir. Right. The absolute last thing that we're going to introduce here, and that's because it's important, especially for these tight unconventionals, is a term that SPE defines as the solution CGR or OGR, and the symbol for that is the little rs. In a lot of industry softwares, it's referred to as the vaporized oil ratio, typically with an like a big RV. In Whitson Plus, you'll see that we use both. We try to use both throughout the software. And so if I went into this guy right here and we looked at, yeah, that was actually not an oil, but yeah, but here you see we actually try to use both symbols just for people to make it easier for people. But what it does is that it quantifies the condensate in solution with the reservoir gas, and it's relevant for both wet gases, obviously, because a wet gas will have some condensate in solution. It's also relevant for a condensate. And then a lot of people don't realize that it's also relevant for oils. And why is it relevant for oils? Because as you go below the bubble point, gas is coming out of solution, and that gas will have some condensate in solution. Okay, and whether that's a very black oil, maybe that's not a lot, or if it's a near critical, more complicated fluid, then there might be actually a big number that, or that the RV is a big number. So it's relevant for both gases and reservoir oils. The units is barrels per million. That's the most common, and the symbol used by SPE is little rs, or in the industry, many places it's RV, and we are going to use them interchangeably through the course today. Good. Any questions before we continue? I see a beautiful picture of the base. Is that that's Victor in Midland with SPE book? I love it. Good. Just let me know if there's anything else that comes up here. But now we're going to go over to PVT fundamentals, and at the end of this this slide deck, there's an exercise. So everybody needs to be on their toes to see if you've actually learned what we're going to go through now. And that exercise will require everybody to write their answer in the chat. So hopefully that'll get you a little bit on your toes. The PVT, as was mentioned, has an impact on essentially every single discipline in the petroleum domain. Reservoir simulation, RTA, PTA, pipe flow calculations, process, reserves, facility design, even drilling operations, et cetera, et cetera. And it makes sense, like, fluids of oil, gas, and water and their properties matter, because we're essentially exposing it to a wide range of different temperatures and pressures when it goes from the reservoir to the sail point. A very, very important concept to grasp is that 1 barrel is not equal always to 1 barrel or one cubic feet. And what do we mean by that? Of course, volumetrically it's the same volume, but what it contains is not necessarily the same. And if you think about it, it's kind of unique. Maybe there's other good examples of it too, but like in oil and gas, when you're talking about a volume, you're placing a context next to it. Have you thought about that before? Like, we were talking about a reservoir barrel, we're talking about a separator barrel, and we're talking about a stock tank barrel. And of course, the volume here is the same, but the amount of mass, density, composition, and of course, monetary value, they're different. So here, if someone asked me, and I would like you to think about it, here, this is not the exercise, but I want you to take 10 seconds to think about this, and I'll give you the answer in 10 seconds. If you had a choice for let's say just a reservoir oil, let's say, but just to give it a number, doesn't really matter, but let's say it's 1,000 scuffs per barrel, and you got the choice, and here the gas, this is in the place where the gas has no value. Would you pick 1 reservoir barrel and 1 separator barrel, or 1 stock tank barrel in that scenario? I just want you to think about it. I'll give you 10 seconds. And it's really fascinating, honestly, at least to me, and I think that's one of the reasons why PVT is so interesting, but also so important to understand. You can hear horror stories of people buying full assets where they have created type curves and they've conducted DCA on the separator rates, and then they realized later that the shrinkage from separator to stock tank was 25%. And you hear these things all the time. And my point here is, if I got the choice and I wanted to make the most money, and I got the choice between these 3 different things, I know that for, there will be a pretty large shrinkage from reservoir to surface. So I would not pick the reservoir barrel. From separator will be a smaller shrinkage for the same volume, but still it will be less than what a stock tank barrel is. And stock tank barrels, that's where I sell my fluids. If I wanted to get a full value or the most value out of my stock tank barrel, I would pick, one stock tank barrel because there's no shrinkage. Okay, so that's the context piece. The second thing that a lot of people don't realize is that these PVT properties, they are actually what's called process dependent. And that's where things are getting crazy and even more interesting. What we mean by that is if you're dealing with, this is like an offshore field, but it's exactly the same for onshore field. If I take a composition and I try to produce it to surface, the final product volumes, they depend on the pressure and temperature conditions and the path to get there. So let that soak in. So the final product, so oil and gas, depends on the pressure and temperature and and conditions, or the pressure and temperature conditions and the path to get to where they're going to be sold. So for instance, PVT properties like GOR, information volume factor, that I'm almost 100% sure that a lot of you guys, that you think about them and you think about reservoir stuff. I think that's what a lot of people think about. Formation volume factor, yeah, that's reservoir barrels, how we convert it to reservoir. And when we think about it, typically related to stuff that's happening in the reservoir, but actually the stuff that's happening on the surface can change what those values are. So if I took an extremely complicated process and I invested a lot of money into a very, very advanced surface process, like you're looking at here, I would get way more liquid oil that's worth more money compared to gas. So more of those molecules will go into the liquid stream. So my GOR will be lower, and my formation volume factor, quote unquote, inverse of shrinkage, would also be lower. Okay. If I did the total opposite and I just took the fluids and exposed them to surface, I would get the least efficient process, and I would get a much higher GOR and also a higher formation volume factor. One thing that Curtis did when we took his class in university was that I think he took isobutane, and he did an exercise where he said, okay, isobutane, it's one of these, I guess, yeah. So you chemistry folks knows what isobutane is, but he took that molecule and basically said, what if we assume that this molecule is going into the gas phase, and we calculated monetary value, and we take the same molecule and we assume that it's going into the liquid phase, and we're calculating its monetary value, and you compared it. And I'm pretty sure when we did that exercise back then, that it was almost like an 18x or a 20x difference. And that's of course a function of what the price of oil and gas is, but I wouldn't be surprised if it was still in that order of magnitude. So these things make a lot of monetary difference, and it also make a big, or it can make a big difference for us as engineers. Also, the conditions again matter. Okay, these are stock tank barrels. What if I actually went in and measured this at separated conditions instead? So for a complicated process, I'll get a low GOR, and for a very simple process, I would get a higher GOR. And then if I, for some reason, just reported the separator rates and sent that to someone to do analysis, okay, I would get the separated GOR, but that's not the stock tank GOR, and that would be a totally different number. So the main point here is that PVT properties are what you call path dependent. And how complicated or simple that path is will dictate also how much monetary value you'll get at the end of the day. So now over to the exercise, a little quiz. I want you to take 30 seconds, look at this composition where this is a reservoir fluid. A question we many times get here, what is the reservoir temperature? That's a great question, but let's just assume it's a typical reservoir temperature that we're dealing with. So let's say 200 Fahrenheit. And I would like you to guess, is this a reservoir oil or a reservoir gas? And you get 30 seconds, and then you need to deliver just your answer in the chat, and I'm gonna put it up here, okay? And I'm gonna go, water is my favorite, so that's what I'm gonna guess, okay? Yeah, a lot of water, no, not a lot of water. Oil, okay. A lot of people on the oil train. Someone bold enough to do gas. Looks like a lot of gas in my opinion, but a concept. Gas, okay. getting gas. Okay, so we have a good mix of both. Very good. Okay, so I'll with that I'll go ahead and give the answer. So obviously this was a trick question. We do many times in these courses. And the trick here is that you will obviously see that there's a lot of methane here, and the mole fraction is just 0.24%. So that's the number of molecules. But if I ask the same question and I converted this from moles to mass, like we did here, and you would see, 78% of the mass is actually C7, and all of that stuff is typically what makes up a reservoir or a stock tank oil. Maybe I'm sure all the gas people would assume that this is a reservoir oil. Okay, and there's so much information in this C7 plus part of the data. And that's a very, very important thing to understand. It's what you call heptanes plus, and it's really good correlated to fluid systems. As an example of right here, this is just put together from Equinor for all their different fields, and you can use that as a rule of thumb to classify reservoir. So you can use GOR. That will be your initial producing GOR. These are rules of thumb. And then you can look at also C7 plus if you'd like to do that. Here, this is kind of like a Whitson rule of thumb type of reservoir fluid classification. There's a different one from Schlumberger. There's a different one in SBE monograph that Curtis wrote. McCain has one. What you need to understand is that these are rules of thumb. If you go and you take a fluid to the lab and the data quality is good and it measures the dew point, it doesn't matter if the GOR is above 100,000. If it has a dew point, it is a condensate. It's just very lean. Okay. So at the end of the day, of course, the data dictates, but these are rules of thumb, and hopefully it can help you a lot in your life. So a lot of people screenshot this. A lot of people use this this slide just for any questions before we're going to go through this piece. Hopefully everybody found out that we're dealing with an oil. Yeah, very good, very good. And for all of those that are struggling with logging in, just reach out to me in the break. We'll take a break here in 12 minutes. So we introduced reservoir fluids, and this is important for you to understand. Like at the end of the course today, a 1,000 GOR fluid, a 3,000 GOR fluid, a 10,000 GOR fluid, and 100,000 GOR fluid. Those numbers should at least give you a gut feeling of what this fluid is. 100,000 GOR fluid, it will never be a black oil on any planet, type of thing. So you need to have those rule of thumbs baked into your portfolio of knowledge, if you like. When it comes to the classification of reservoir fluids, we're going to go through the official classification of that step by step. And those are typically dry and wet gases and condensates. And we have volatile oils and black oils. In between these two guys, there is something that typically is called near critical fluids. Okay, and we'll talk about that. What is the critical point? What kind of defines it? What makes it unique? And sometimes you're dealing with, like, you say it's a collection term for near critical fluids, or you say it's a near critical volatile oil or a near critical gas condensate. So we'll talk about that. But that's just an FYI that in between here, you might be dealing with something called near critical fluids. So if you look at the fluid classification, if you go by that step by step, the classification of reservoir fluid systems, that's determined by the location of reservoir temperature with respect to the critical temperature and the so-called Cree-Conant term. We'll talk about what those two items is. And the other thing that actually matters is the location of the first stage separated pressure and temperature with respect to the phase diagram. And that's like, wow, that's a little bit mind-blowing. That the location of something that's happening on the surface is actually relevant for what's happening also in the reservoir. I feel it's a reservoir fluid classification, not something related to surface. But that's actually a very important point. And maybe after this, I'm done with this. Maybe Curtis can take the story about white oilers as we at least go through this and end up with a dry and wet gas. The first thing we're going to do is to look at the black oil. And again, it was two things that mattered. Okay, where is the reservoir related to this point right here. That's the critical point, okay? And then there was another thing that's called the Creconen term. And the Creconen term is just the maximum temperature on this phase envelope right here. Okay, so it's basically this line right here, and is this point right here. And that's it. In this case, we're to the left of the critical point, and we're now dealing with green points. That's what we call a bubble point. And as we reduce the pressure, we hit the bubble point, and then gas is coming out of solution. So if you look at a liquid relative volume curve, which you're looking at here down to the right, or I guess at the bottom of the screen, of course, the liquid relative volume is 1 above the saturation pressure. And as you go below the saturation pressure, that number becomes smaller and smaller because a lot of it is becoming gas. That's a pretty linear relationship for a black oil. So what about a volatile oil? Well, it's still the same. What you can call it. The two things are still important. That's the critical temperature, and it's the Creconen term. But the volatile oil, which you'll see, will be closer to the critical point. Okay, so that will be, for instance, here. Typically, it has a higher GOR, so it will also have a higher bubble point. But in a similar sense, it's only liquid above the bubble point. It is still exhibiting a bubble point, and the liquid relative volume above the bubble point is 1. And as you go below the saturation pressure, the liquid relative volume has not a linear shape now, but more of a curvature to it. And that's at least how we internally kind of distinguish between a black oil and a volatile oil. And a lot of people, rule of thumb basis there is around 1,000 scuffs per barrel. That's when you start to see that shift. And that's also the logic that's used in Whitson Plus. And of course, it's a little bit arbitrary that we picked 1,000 scuffs per barrel, but it could be 1,100 or 900. But we like round numbers, okay? But if you want to take this to the lab and kind of see if you see curvature here on the shrinkage curve, well, then it typically means a lot of gas is coming out of solution. And the steeper that curve is, the closer you are to the critical point. And at the critical point, that thing will be almost vertical. Then we're dealing with a retrograde gas condensate, and then we're on the other side of this, what's called a critical point. So that's the critical point is again this guy right here. And it makes sense to talk about what is the critical point right now. So the critical point is the point where both the properties of oil and gas, they converge, and you can't actually distinguish and say whether it's a gas or an oil. So what does that mean? Well, if you looked at densities, formation volume factors, viscosities, compressibilities, saturation pressures, all of those properties converge and they become the same number at the critical point. So you're basically transitioning from being a near critical oil on this side to being a near critical gas condensate on this side. And if you want to think about it simplistically, any gas, any reservoir gas with a dew point, that's by definition a gas, the gas condensate. How do you know it has a dew point or a saturation pressure in general? Well, if your GORs is changing over time, it's a really good indication that you're actually are hitting some kind of saturation pressure, even if you're super, super, super lean, right? So now you're on the right side of the critical temperature, but you're also on the left side of the Creconen term. So you're in between here. You're in between this little range, and that's the definition, or that's where, call it, these gas condensates are living. And above the saturation pressure, the dew point, there is no liquid, right? There's no liquid right here at the bottom. Just try to use the laser pointer. Here, there's no liquid because it's vapor when you're above. So when you're above up here, there's no liquid. And as you go below the saturation pressure, condensate is dropping out of solution, and you get a liquid dropout curve, which is what it's called, that actually is what you call non-monotonic. So it decreases before it reaches a minimum, and then it starts to go up again. And that is something we'll talk about later. But you have a condensation driven part of this, and also a vaporization dominated part of it. And this is linked to what we talked about earlier, K values. And that's the second time you hear it. We'll talk about that later. And that's very important to understand this shape. And it's also very important to understand, the shape of the solution CGR curve right here that I'm sure a lot of you guys have been looking at. Like, why does it go up there at the end? Well, This is a teaser, as we call it in Hollywood, and something we're going to talk about later. Then wet gases, that will be a gas that produces liquid at surface, but it doesn't have a dew point. So the GOR should be flat over time. The compositions that you're producing should be constant, okay? But you're still producing some hydrocarbons. So that will be over here to the right. And you will also have a surface process that's inside of the two-phase envelope, because the surface process needs to give, or the separated temperature and pressure at surface should give you two liquids, a separator oil and a separator gas, or a stock tank oil and a stock tank gas. Okay, but in the reservoir, since there's no dew point, you know, there's no liquid in the reservoir at any point. It's just single-phase gas in the reservoir, but at surface you're actually seeing two-phase. And then we're dealing with a dry gas, same thing in the reservoir, no dew point, but at surface, the surface process is outside of the two-phase envelope. So there's no liquids being produced at surface. And that's also why you're dealing with that's not related to this, but just like with a dry gas and a wet gas, there's no liquids dropping out in the reservoir. So the liquid relative volume is zero. So to summarize this, if you look at a volatile oil, initially you're 100% liquid. You go below the saturation pressure and gas bubbles form and they rise, and you have a free gas phase and a free oil. And typically the gas is more mobile than oil in general, and vice versa. For a condensate, the opposite is happening, where the above the dew point is 100% gas. As you go below the dew point right there, oil droplets or condensate droplets, they form and they fall. And then as if you stabilize this at some lower pressure, there'll be a free gas phase and a free oil phase. Many times the mobility of that oil phase is extremely, extremely low. Great. Second exercise today. Now we've learned about all these beautiful definitions. Victor, that has his SBE phase behavior monograph up. This is a table from the SBE phase behavior monograph. And it has one typo in it. And I would like you to take a close look at this table. If you've done this exercise before, you're not allowed to answer in the chat. But if you have not, I would like you to take a close look at it and suggest what is, considering what you learned now about reservoir fluid classification, what is not right in this table. And then for people with the book, can look up the table. I think it's in chapter 2, and then you could make that fix, or at least make a comment about it. And I see we have some questions here too that we can touch upon. Yeah. Okay. Did everybody understand so what is wrong with this table? And then we will also do the questions here that Kurzov mentioned too. But anybody have any suggestions? You can unmute. You can write here in the chat as well. Okay. Dry gas methane is low. C1 is very high for wet gas. Are the dry and wet gas C1 content switch? Okay. Yeah. Good observations. Could that be the case? So go back to the definition. The definitions of this. Okay, excellent. So hopefully at least you've thought about it a little bit. So just to repeat the high level parts of the definition. If you have a bubble point, if your saturation pressure is a bubble point, it's a reservoir oil. If it has a dew point, it must be a reservoir gas condensate. And the definition for a wet gas and a dry gas is that neither of them have a saturation pressure in the reservoir, and that a dry gas doesn't produce liquid at surface while a wet gas does. So the error here is just this saturation pressure here for wet gas doesn't make sense. It shouldn't be here, this number, okay? Around 3,400, because a wet gas has no saturation pressure. And then to your questions or the comments here is that C1, so the dry and wet gas of the C1 is switch. And then you need to ask yourself, does that actually have an impact on the definition? So the components that actually translate into stock tank, like the stuff that goes into your car, that's typically stuff that's heavier than C5. And that's what will translate into liquid. So that's the stuff right here. And you see the wet gas actually has a lot of stuff that's heavier than C5, and so naturally we're thinking, okay, that actually can translate into to some stock tank sellable oil, for instance. Well, this guy basically has nothing, especially nothing that's higher than C6. Very good. And just to a couple of the questions in the chat. The first one, which we get a lot, that question is this revaporization of that we mentioned here in the condensate slide. Let me just here we go. So what's happening here is revaporization. Is that actually something that can be observed in real life, or is it just a lab phenomena? That's what Tarun asked, and that's a super good question. And Curtis answers that the gas condensate reservoirs depleted to very low pressures. So that means to be like a few hundred psi's will show an increasing producing CGR. Yes, but it's not a big economic factor because the producers are often at so low rates late in life that both gas and oil rates are low. But the relative amounts start increasing and will continue to increase as depletion continues. Okay, so we can observe it in life, but typically has a very little economic factor. And then I think
so, guys, I think.
Yeah.
Sorry to interrupt, but I think the critical saturation for the condensate also would come into play, right? Like if your saturation in the reservoir is below the critical saturation, then your condensate is not going to be. No, sorry. This is for liquid. I take my comment back. Sorry.
Yeah, so I think, even if it's below the critical condensate saturation, right, that won't be flowing. But what will happen here is that this is the gas phase that will actually carry that. So that will vaporize that condensate back, that it might even be below the critical condensate saturation, back into the vapor phase. And it's the vapor phase that's actually transporting this up to surface and it's being produced. But it's a good, I see where you're coming from, Tarun, on that. And then I think also we had a question from Chris. In a retrograde gas condensate system, do you know what's happening on an intermolecular basis to cause a portion of the system to liquefy when the pressure is dropped below the phase envelope? And Curtis answers, the K value pressure dependence of heavier components, which is C7 plus, will dictate whether oil condensates out of gas as pressure declines, or whether the oil vaporizes back into the gas phase as pressure declines. And he also mentions a few rules of thumb there that we'll actually talk about later. So that's good that these questions are starting to spin in people's mind now, because they're really, really relevant for what we're going to talk about. Curtis, you're still there? Maybe you're muted. Let's see here. Maybe you had to leave. Okay. What we'll go ahead and do now is we're going to take a break, and then we're going to be back in 9 minutes, and we're going to continue after here. But now you guys know a lot of the basics, and in the break, I'm going to make sure that everybody can log in, at least the ones that hasn't been able to. Excellent. Okie doke. People just give a I don't know, a reaction or something if they're back, a clap or a note in the. Oh, there we go. Like it. Gonna give people 30 seconds there just to get started. What we're gonna do now is gonna be fun, and we've never done it in these courses before. Yeah, it's pretty. It's tough. It's tough in the PVT world. Like 9 minutes is what we get, but I'll make sure that the next one is longer. But you know, as you get later in the day, we'll make sure that they get longer. But we'll give people 10 minutes. I can do a joke in it meanwhile. I don't know if I have a good one, but it's Valentine's Day at least, so my girlfriend brought me a cup of that told me that I'm a fantastic boyfriend. So now I have that proof at least. So I'll make sure that I'll live on that throughout the whole day today at least. She's lying. She probably is, but it even says on the cup that those other boyfriends, they're total losers actually. So anyways, but if she wrote it down on the cup, I mean better be true. Good. So we'll get started here again, and we'll talk about fluid initialization. And this is a brand new part of the course that we're going to do kind of in a case study format. We're going to talk about fluid initialization, like how do you actually initialize a model once you have an equation of state model built. And we'll talk about the details of the equation of state later. But this is really important because that's typically what the people in the company will be doing on a day-by-day basis. I see, Joey, you have your hand up. Do you have a question, or was that just to say that you're back? Okay, I'll interpret that to be the latter. Goody. So we're going to just continue here with the fluid initialization. And this is related to probably the most important goal of the whole class, is to be able to use readily available data, specifically producing GUR or CGR, to initialize the reservoir fluid for an unconventional well. Okay, and that's most of the kind of the cookie cutter usage of the PVT feature. And there's more advanced features too, but we'll focus on the GUR feature today. And we're going to do exactly the same thing as Steph Curry. I'm not big into basketball, but I heard that this guy is like the world's best 3-point shooter. And when you listen to how much he practiced it, he was doing 500 3-point shoots a day, which means that it's around 200,000 shots per year, which is, again, if you want to be good, you need to repeat. And that's actually what we're going to do now. And I've never done it before, at least live like this. We do this all the time for more offset things. But what we're going to try to do is I'm going to try to provide you with some practical wisdom in general, and some rule of thumbs that I really think that you should know when you're dealing with PVT in tight unconventionals. The first thing is to try to rewire your mind to still think about phase envelopes, but not think about that PT phase envelope. That's like PVT 101, That's what you learn about in school, vanilla envelope phase envelopes. You want to be more of a saturation pressure or a pressure composition phase envelope guy. And that's what you're looking at right here. So in this case, it's the exact same thing as what you're looking at for a phase envelope. Inside of these two lines right here, you have the so-called two-phase region. This is also plotted in log scale, by the way. So this would be like maybe 100 scuds per barrel, and this would be maybe 100,000 scuds per barrel. And in between here, you have two phases. And outside here, just like with a phase envelope, you have single phase oil, single phase gas. The difference is that in this world right here, this is plotted for a constant temperature. And this is actually, when you're creating a black oil table, that's actually what's happening. It creates a full table like this, because a black oil table is generated at a constant temperature. And at least for reservoir activities, your temperature is not really changing. And on a relative basis, like the change in temperature from well location to well location is not as big as your changes in GUR and pressure over time, if you look at that. Okay, so the practical wisdom is that you should use the producing CGR or the GUR to help you guide and tell you a lot of stuff about the well. And that's one of the first things I look at. Just look at the producing GR over time. What does it do? Is it flat? Does it increase? Does it increase immediately? Is it linear? Is it flat and then it shoots up? There's so much information there that you as an engineer, just by looking at that thing, you know immediately something about the well. And if that's stuff that you're starting to look at for many of the wells here, or if that's just an outlier, okay, then you know that maybe this is something special going on with this well, or maybe it's just consensus. So in general, this is a general guideline. As we're below the saturation pressure, the GOR we should expect the GOR to increase. That's in general. There are exceptions to that we'll cover. If you're dealing with a wet gas, you know that your CGR or GOR needs to be constant over time because there is no saturation pressure. And if you're not producing hydrocarbon liquids, you know you're dealing with a dry gas. So that's basic. But then I would like you to remember this one. And this is very, very, very nice rule of thumb that actually I've seen to be a good rule of thumb in any unconventional basin. Maybe it's up, a few hundred scf per barrel or so, depending on basin, etc. But the critical point is typically around 4,000 scf per barrel or 250 barrels per million. So if you're dealing with a well that comes online with an initial producing GOR right here, you know that you're dealing with the most complicated type of fluids. And that's where, an equation of state is definitely needed to create those type of relationships, because that's where all the correlations break down. The correlations typically work well up to 1,000 scf per barrel. And, if you read the papers, that's typically the data set that have been used. Or dry gases is, of course, a different story. Okay, so as soon as you see numbers that's in the 3 to 5,000 range, you're like, oh, that's near critical stuff. That's stuff you should know. If you see that GOR is 4,000 scf per barrel, okay, this is close to the critical point, and this is complicated stuff. And then it kind of gets easier as you're moving, and that's this point right here. It's a critical point. And then it kind of gets easier a little bit as you move away from it. Low GOR oils, more predictable, lower saturation pressure, not that much gas coming out of the system. The leaner you get here, the less condensate actually dropping out of the or dropping out in the reservoir, etc. Okay, so this is where the party's at. And if you look at some of these basins, some basins doesn't really have a lot of narrow critical fluid in situ. So if you think about Bakken, for instance, probably the most volatile you have there in situ is probably 2,500 scf per barrel. But in a lot of the other basins, you will actually see that you have fluids in this whole range. Permian is probably the best example where you have, especially on the Delaware side, I feel like most of the samples is probably in this region. There, could be near critical fluids, etc., which makes it extremely complicated to model. So that's what we're gonna talk about. Perfect. So we're gonna think about this stuff right here. The red points, that's dew points. The blue points or the green points, they are bubble points. And what we're gonna do, we're gonna go through 20 case studies. And I understand that will take a little bit of time, but we're going to go through 10. We're going to do what Curry does, and we're going to repeat. We're going to start at the starting point here. We're going to move our way upwards on this trend. We're going to, take a turn here, as we say, in race car driving. I'm pretending that I know stuff about a car. I don't know anything about cars. And then we're going to go here leaner and leaner and leaner. We're going to end up with actually a dry gas. Okay. All of these wells is 100% real data. We're going to start with a low GOR fluid. We're going to move our way up. So they will have different things related to them. And then but they're going to be, and they're going to show a lot of the data quality that we work with. What kind of data quality are we actually working with? Well, that's the first thing that we're going to talk about. And you'll see it. And then there's different tricks that we can apply with. Great. So we're going to start with case study 1. It's going to be fairly easy. And this is a screenshot from the software. I'm going to use the software. You're not going to do this, but we're going to do it together. So I'm going to share the screen, and I'm going to pick a line, at least how I would do it, because this is probably the question I get the most. How do you actually pick an in situ representative GOR? And the first rule that you should learn is you don't want to pick a GOR, especially doing cleanup and stuff, that hasn't really stabilized. So you would like to try to look for a stabilized producing GOR. That's not affected by cleanup or stuff like that. So that's the first thing you should look at. And also, if there's a period before you drop below the apparent saturation pressure, you should expect that the GOR is constant for a period of time. So we're gonna pull up case study number 1, and I have prepared that in the software, and I'm just going to use the PVT feature, and that's what we're going to do here later as well. So when I open the reservoir fluid composition card, and if you've not done this before, I know some of the guys on the call have done this a billion times, but if you've never done this before, you click here up to the right. and that's where you can change the initial producing GOR up and down. Automatically, the software will have zoomed into the first 100 days on the GOR, and in this case, I'm only going to use the GOR method, and that's to make sure that you hopefully learn some stuff. And then as I drag this over, I see like, okay, eventually this thing is going below the saturation pressure, and GORs are changing a lot. Okay, but my job as an engineer is to try to find, okay, what is the in situ representative GOR, and I can drag this line up and down. Maybe I can do this. I can drag this line up and down, and that's connected to my data point here. And I can also use different toggles depending on what I'm trying to do. If you're really noisy, using cumulative GOR up and down like this could make a lot of sense. And I think I had picked a number, and I also like round numbers, around 330. So now you've seen this. This is data quality. It's actually kind of good data quality. And I'll click save, and I'll let the software do its magic. And if this is the first time you've seen this type of calculation in Whitson Plus before, what it does is that it goes in, predicts a fluid composition for us for this fluid that is used to generate this phase envelope right here that we talked about. And you've learned now about the reservoir fluid classification, so you know now we're on the left of the critical point, and we're seeing bubble points here. This is the reservoir oil. Everybody knows that. So it creates the phase envelope with the equation of state in the background here. This is just a default equation of state. Same that we're going to use is available in the software. And it uses that to automatically create the tables that we can use in any third-party tool or everywhere in Whitson where you need PVT tables for that type of job. So here we see it's the black oil. Bubble point is around 1600 psia. The GOR is what I inputted. That's the solution GOR, 330. And it's an initially undersaturated oil. That's the reservoir type. Okay, we're starting easy. That's good. Case study 2, that is a little bit higher GOR. So that's what we're going to do here. I'm going to go to the next well, 350-ish. So we're saying, okay, a little bit higher GOR. What should you think immediately? Well, okay, a little bit higher GOR. What happened with that curve, the phase envelope curve? The points went up, right? So the saturation pressure, you should expect that the saturation pressure also goes up a little bit. Here again, this is amazing data quality. Eventually we go below the saturation pressure, but it looks really, really, really clean. You might want to look at this in CubeSpace if you like. In this case, I'll just click, save on 350. Makes me feel really good. The software would go in and predict the fluid composition for me, like this. Create the phase envelope that we're looking at again, and the tables. And now you see it went from 1600 to 1700, which is what I should, in general, is what I should expect, right? So back to this, I started down here, and now I moved a little bit along the line here. Okay, so small baby steps for starters. But this is the mental picture that I would like you to have in your engineering toolkit, because it's really relevant. Okay, so now we're going to take a little bit bigger leaps. So we're going up to almost 600 scuffs per barrel. So saturation pressure should start to change a lot. Also, this case has more complicated data. It's around 600, so that's what I'm dealing with here. Temperature and stuff is changing a little bit. And you see very early goes below the saturation pressure. Initially, it has a period where it almost starts at 415. Everybody sees that. Some people come to me and say, but that's the initial producing GORs, they will put it here. But in this period of time, there's a lot of cleanup happening, and there's other parts where you can check that in the software what's happening with the other rates. Like in this case, the water cut is really, really high initially, for instance. So I like to use this view a lot. But your job is to find the stabilized portion of the data. Here, it looks like it hits some kind of saturation pressure. You see a steep change in your GOR. So personally, I would probably pick this number somewhere around 600. I'm a round number guy, so I'll put in 600, and I'll ignore this initial piece of data. And doing this will be very important if you bring this in to, for instance, a history matching exercise. And again, what should we expect? GOR is a little bit higher. What was the saturation pressure for the 350? It was around 1700. Now we're seeing what's happening with the phase envelope, right? This is the phase envelope. So this is like we take a slice of this this other phase envelope that we looked at, and we look at it in the pressure temperature space. And we're seeing this point is getting closer. We're getting closer to the critical point. So what will happen, so the conditions will be kind of the same, similar for all the wells. And then at this point, we'll start to move to the left. Saturation pressures, 2,400, okay, a little bit up. So we're gonna do, continue to do this, and now it's gonna get more complicated. We're gonna do a well that has a little bit higher initial GOR, like this. Again, here it has the opposite trend. Clean up from the top, and then it stabilizes over a period of time. It hits saturation pressure clearly. You should ignore the early time data here, and you should go in and pick that part of the data that's stabilized. Okay, this is bogus. This is bogus. Clear and situ representative trend right here. And again, I can move this guy up and down, or I can just use what I had, which was a beautiful number, 750. I can click save. And again, the process is the same. And now we've moved kind of far up on that PT curve, getting a little bit more closer. And we'll see that our saturation pressure now is getting even larger. So if I plotted those GOR points and the bubble points, if you like, we would see that we would get further and further along this plot right here. But I'm still, 750, still pretty low. So I would like to take this for a spin and go, even to where it becomes a little bit more fun. Maybe I jumped a little bit ahead here. Let's see. Okay, perfect. So that was number 4, and we're gonna go to number 5. This one has a very similar thing. This is around 1,000. That'll be this guy right here. Has pretty low GORs in the beginning, stabilizes before it goes up. So many times it can be really helpful to actually look at the data. And this is like clear saturation pressure is being seen. GOR looks like it's close to 1,000. I'm just going to use the GOR method here, and not the GOR and API method, and I'm going to run the same calculation. And we're getting higher saturation pressures. Earlier we had around 2,800 or so, and we should see some. Now we should be higher than 3,000. Moving along, we'll see. Okay, 1,200 scf per barrel. That'll be here. Here we see we have an outlier data point early, so I can go in and zoom in to 2,500. We hit saturation pressure extremely quickly here. Maybe this is a good pick, or maybe I could go even a little bit larger. Here it looks like it's actually doing a little bit of a dip before it increases. That we'll talk about in a sec. But this gives us 1,200 scf per barrel, and I should now get an even higher saturation pressure typically. And now you see the phase envelope. Interesting. Still in this region, and now our critical point is moving a little bit more to the left. Okay, and now we're going to get into volatile oils. So if you went into these definitions now, you'll see volatile oil. So we crossed 1,000 scf per barrel. Now it starts to classify these as volatile oils. Right. So now there's a couple ones that's like more in the 1,600 range. That's these numbers right here. These are interesting because they're very noisy. So you see here in the beginning, it might be really hard to find values visually by just looking at this. And this is where the cumulative GOR can be really helpful to guide you and why is that important? If you want to use this for any engineering exercise and you want to history match your cums and stuff, if you would be off, if I would pick 1,000 here and then it's more, 1,500-ish, something like this, then you will be far off on your history match. So maybe some of you guys would pick a number that's maybe even a little bit higher here. Maybe 1,600. That's a good maybe that's a good pick for this guy. And again, our saturation pressure, we should expect them to be larger. And now we're getting even closer to the critical point here, and our saturation pressure now is 4,000. So we're seeing getting closer and closer and closer to the tip of that nose that we looked at earlier. Excellent. Now we're going to go to the second most close sample to the critical point, and that's this guy right here. The initial producing GOR, you can just do that to 5,000, drops below the saturation pressure really quick, really fast, and it actually stabilizes here for a period, which is very typical if you have like an infinite acting well that's still infinite acting, so it has this infinite acting plateau for a period of time. And I would probably pick a number, maybe even zoom into the first 20 days, and then use either the average of these. Here I see the scale is kind of crazy, or use the cums or something, maybe something like this to pick the in situ representative GOR. And that's And now we should see that the critical point is getting really, really close to the left here for our well. We also see now that the undersaturated, the realm or the headroom, if you like, will be lower and lower because your saturation pressure are increasing. The phase envelope started, down here, and then it moves up and to the right, if you like. But this is what you would call a volatile oil. You see, the more near critical you are, the more shape and more curve to this guy you get. And now our bubble points are really, really high as well. So the second closest, okay, we can do the 4,000 scuffs per barrel well. This is actually a Wolfcamp camp well, and it's so close to 4,000. Here you see something that's we'll talk about later, almost an linearly increasing GOR. But again, here I would pick a number, maybe using this cumulative GOR button to pick a number around 4,000. When you click save, you see how close we are to the critical point. We're not exactly on top of it, but if I made this, 4,000, say 4,300, and I'll push that a little bit further to the side, you'll see that probably will be almost just on top of the phase envelope. Yeah, exactly here. This is almost a critical fluid on top here. So if I use this and I went to the PVT table, you'll see that the formation volume factors, they're almost vertical in the beginning here. So if you're in that realm that I talked about, that around 4,000 scuffs per barrel, a little warning lamp should light for you. Anyways, when I'm far away from 4,000, so now we're getting into the latter part of these case studies. So I'm looking at a GOR here that looks to be around 6,000. Again, ignore this early data point. Use cum GOR as your friend. And here, if I drop this over to around 6,000, I would then know. Okay, I know already that this is a gas condensate, but it's probably rich gas to gas condensate. I don't even have to run it. And why do I know that? Well, I know it's far from that number that we just talked about. That was 4,000 scuffs per barrel. It's like a GOR of 2,000 scuffs per barrel. I know it's a volatile oil and not a near critical fluid. Now you see the saturation pressure has been lifted. This is also a what you would call a saturated fluid, or a two-phase saturated fluid. On a relative basis, you have much less of the C7 plus that we had earlier. And sometimes these phase envelope are just giving us dew points, and the critical point is actually over here to the left. And in this case, this is interesting because it's what you call a two-phase saturated system. So in situ, it predicts that it actually has a little bit of oil or free mobile oil saturation and gas saturation. Now, that's something we see many places, especially in the Montney, Scoop Stack, and parts of the Permian. Great. And then going further along here to higher GR fluids, then we know that we're getting further and further away from the critical point. So now we are on the other side of our friend. So we went, this is the critical point right here. Then we started to actually follow this trend going backwards to the end here. So now when we're increasing GOR, we should actually expect our saturation pressure to decrease. So now we're dealing with a 6,000 scuffs per barrel fluid. And if I bring this back into to something that's more around maybe 13,000 or 14,000, and I click save, here it looks like this is stabilizing around here. So I agree with that. That pick is pretty good. I should expect, okay, it was like 6,000 or 5,000 in terms of saturation pressure. Now you're seeing the headroom is coming back again. My dew points or my saturation pressure is, probably 4,700. So that will start to go down. That's also what will happen if I take an even leaner well. So you can take 22,000 scuffs per barrel. Really interesting well that we're dealing with right here. This is a little bit choppy data, but it increases almost from day one. We'll talk about that in a second. So if I make that 22,000 and I click save, you'll see that the saturation pressures will continue to go down in the PVT table. And now you see all the points here are red, and now we're getting in the 3,000 realm on the dew point. The second to last run, this is a very, very lean fluid. So lean that some people probably would just say, okay, this is a gas, or this is a wet gas. But here again, saturation pressure here for this well, it is changing. It's initially 75,000, 80,000, and then it goes up. And unless this is a measurement issue, if this is a real reservoir response, you know that this should then be classified as a very lean gas condensate well, okay, around 70,000 scf per barrel. If we made this prediction right here with the equation of state, we'll then see, okay, are we actually dealing with a wet gas or a very lean gas condensate? And here, we're just dealing with a very lean gas condensate. We're further down here, so you see that the dew point should be lower and lower and lower. Saturation pressure is here, and that's what we're seeing here. Very low dew point, around 2,000 scf per barrel, or 2,000 psi, and that's what we're dealing with right here. The absolute last one is a case where, you know, if the only things that you're producing is gas and it's water, then you need to use something that's not, and it will look like this in the software. You need to use the dry or wet gas composition method. Then you can input a specific gravity, for instance, 0.6, and then the software will predict a phase envelope. It'll be so dry, there's no two-phase envelope right here, but it will still use it to predict a composition, and it will still predict a PVT table for us. That PVT table has no RV, which we'll talk about in a second, but it will just have a gas expansion factor and the viscosity. This is what you call a dry gas PVT table. And back here, we're now at the end. We're dealing with a dry gas fluid in general, has no dew point, and we're probably on the outside over here. So hopefully you've learned a couple of things from this part. Make sure that you find a stabilized producing GOR when you initialize the fluid. Make sure that you know rule of thumb that this 4,000 scf per barrel mark is very important, because it gives you a gut feeling about how complicated the fluids you're dealing with in the reservoir are. And think about this in your mind when you're dealing with different fluids that's spanning a wide range of fluids. You see this in the Eagle Ford, you see this in the Permian, you see this in the Scoop Stack, Montney, Duvernay, Utica, etc., where you have this range of fluids. And if you have this range of fluids, you should expect your GORs, at least on a general basis, and your saturation pressure to follow something along these lines. If you've ever done a swell test in the PVT laboratory, that's basically very, very similar shape to this. Now we're going to go through some. Okay, so I saw there was some questions. Probably should have monitored that. Okay, no, that was no questions. Great. Any questions related to this until we are going to look at a few special cases. This might be good. So don't be fooled by like initial producing GORs that's going up and down in the beginning. That's like low. You should find, you know, the QM GOR is a really good trick to find a number that's in situ representative. Excellent. Now we're going to talk about a few special cases. Special case number one is what we call a saturated reservoir. And what that means is that the initial reservoir pressure and temperature is at the bubble point or the dew point if you were over here. What that means is that, you know, from day one, your bottom of pressure is below the initial reservoir pressure, that you're inside of what we call the two-phase party. So your initial pressure is either equal to the saturation pressure or lower than the saturation pressure. And that makes it really complicated, because now you have three flowing phases in the reservoir from day one. And that's what we call the two-phase party, and you will typically see GORs rising from day one in this case. So the general shape of your GOR curve should rise from day one, and it should look, or that should be the general trend in general. The problem, and what makes it really complicated, is that then your initial producing GOR is a function of relative mobilities. Okay, so I'll take that one more time. So it's not as easy as me going into Whitson Plus, like for this well, and I just said, okay, my total GOR is equal to my solution GOR because the GOR is constant. In this case, my GOR is going up from day one, and my initial producing GOR could be equal to the solution GOR, but it can also be a number that's much lower. And why is that? Well, that's because when you're inside of this two-phase envelope right here, your producing GOR is the function of relative mobilities. The function, or like the equation for that, is this equation right here, where RP is the producing GOR. This number right here is the solution GOR. This is the vaporized oil ratio here, the little rs. And then this alpha term is just the relative mobilities that I talked about. So the rel perm of gas to oil, KRG, KRO, formation volume factor of both phases, and the viscosities. So that's like a relative mobility term. So you see already from day one, it can be kind of complicated because your GOR can be equal to the initial producing GOR, or it can actually be a number that's even lower than your producing GOR. So for a well like that, if it was shooting up from day one, it could be, if you since this actually has some data that's up to 6 days, I'm just going to pretend that this is a well that shoots up from day one. In that case, this could be your pick, or you could have a pick that's even below here, because now it's these relative ratios that is dictating your producing GORs, and that's super relevant in the Permian, in the Scoop Stack, in the Montney, especially those basins where you see a lot of huge parts of the plays are in regions like that. So just keep that in mind. So that's a special situation. Typically, your GORs will look something like this. There's no rest from day one. It just shoots up, and this can be your pick. This can be your pick, or a number that's lower than this. Okay, so it makes it really, really, really complicated. Another case that's super interesting is if you're producing constant, or if you have wells that are producing at a constant GOR, even though your bottom hole pressure is below the saturation pressure. Okay, you've gone below the saturation pressure, but the GOR is still flat. And there's 3 ways to model that at least I'm aware of, and that I'm going to share with you. I'm just going to show you some examples of this too. Okay, and this is not like you've been, if you're above the saturation pressure, obviously for a few days, but this, now I'm talking like you have 1,000 days of constant GOR. That's what I'm talking about, or 2,000. So the first thing could be that you just have the wrong saturation pressure, and that you're producing at a pretty high bottom hole pressure that's still above the saturation pressure. That's very rarely a typical explanation, but that is one in the solution space. The second one, which is a really easy thing to model, or to put into your model, is to have a huge pressure drop between the matrix and the wellbore. And that can be achieved by, for instance, introducing a low fracture conductivity. And then we have a case where you can model this, which is also interesting, and I think it is a very viable explanation in a lot of basins, is where you're actually dealing with a dual PVT system, or one or more fluid systems are feeding into the same wellbore. So a good example of this can be a very low GOR oil that will have a very low saturation pressure, and for instance, a thin rim of dry gas. And together, if you took those fluids and they mixed in the wellbore and you sampled them at surface, they might look like a condensate if I brought it to the lab. And that makes it really, really complicated. So I'll show an example of all of these 3 different scenarios just in the software right here. Okay, I'm just going to change to some synthetic, and I just model these in general. So the base case, that's what you would expect. Okay, this is a well that goes has the saturation pressure is here around 3,200. We see that the well goes below the saturation pressure of 3,200 around 200 days, and that's why the GOR here shoots up at around 200 days. Yes, that's the base case. So that's what you would expect in general. That's what I would expect in 9 out of 8 times. But then you have these wells, as I talked about, that show you this constant GOR performance over time. So one plausible explanation that I think in general is typically not the case, but it is possible, would be that just your bottom hole pressure is high. So in this case, if my bottom hole pressure never got below the saturation pressure, so the saturation pressure was 3,200, and it was always above the saturation pressure, then the GOR will be constant, right? Because now we're always above the saturation pressure here. So the bottom hole pressure goes to here, and not a PSI lower. So you're never inside of the 2-phase envelope, okay? That is one plausible explanation, and that's this guy at the top here. If I took the base case, and now I'm talking about number 2 here, if you have a really large pressure drop between the matrix and the wellbore, for instance, with a low fracture conductivity, that will be this guy right here. So this is the base case. The only thing that I've changed is that I've made the dimensionless fracture conductivity, instead of it being 1,000, I made it extremely low. So that means that it's a huge pressure drop between the matrix and the wellbore. And that's just to exemplify this, that will simulate with not a very complicated model, constant GOR for a long period of time. And this is just arbitrary numbers that I picked, but that's one plausible explanation. And then the last one is what we call a dual PVT system. So you have one layer that is an oil layer, and you have another layer that is, for instance, a gas layer. And that's what you're dealing with. Yeah, this is a good example of that, where I've gone in and I've added 2 layers, a very thin streak of gas, and then a big streak of oil, and then I've initialized the different the streak of gas to be like 100,000 scf per barrel, or is this a million? It's at least very, very low, and then a very low initial producing GOR or GOR of 500. And here my GOR is going down, and you get this, which for all practical purposes is a flat constant GOR right here after it's stabilized. And that's also one way of modeling this type of behavior. Okay. The problem with this is like, okay, if I brought this into the lab, you know, it has 4,000 scf per barrel. This guy, right? It's 4,000 scf per barrel. It's near critical, you would think immediately, right? But down in the reservoir, it's neither. It's basically a dry gas and a very low GOR oil that looks like it's together some kind of condensate. So that is probably a plausible explanation. Of course, very complicated to know and to model in practice. But I think it's a really and Kurt has written a ton of papers on this as well. And we'll actually look at it can be a plausible explanation for even GORs going down. So we'll talk about that too. Special case number three. Okay, if we're dealing with GORs that go down before they go up, that's kind of and that we see all the time. This is an example of that. This is an example of that, where we're basically dealing with what you learn about in school, which is what we call solution and gas drive. So pure solution and gas drive reservoirs are subject to 3 different stages of idealized production. And in chronological order, the stages are you're producing while the well is undersaturated. So as your bottom wall pressure is above the saturation pressure. Production while saturated, but the free gas is immobile. So what happens here is that gas is coming out of solution, but the gas is below the so-called critical gas saturation. So it doesn't move, it just takes up pore space. But since that gas has now left the mobile oil phase, that mobile oil phase has less gas in solution. So here, what is being produced at surface is just that less, or that mobile oil phase with less gas in solution, and the rest is stuck. And then we're reaching the critical gas saturation. That starts to flow, and that basically becomes number 3 here. So your production, while saturated, and the free gas is mobile, and then the producing GOR starts to climb. So what we're dealing with here is this number 2 here. If you see this kink, very easy to model in the software, and I think even my base case had a little kink there. Maybe you guys saw that after, you know, and this is kind of Muscat 101. GOR goes down before it goes up, and that's because I had 5% critical gas saturation. So before we actually reached that critical gas saturation, it will actually start to decrease before it increased. Absolute last case here on this topic, and then I'm going to promise Ole to do a 15-minute break and not a 9-minute one, and that's decreasing GORs. And here again, I'm not talking about decreasing GORs for a little period of time. That can be cleanup with data issues, whatever. I'm talking about decreasing GORs over like 2,000 days, which you're seeing here. Plausible explanation for that could be also a dual PVT system, where and this is for a case from the beginning, where you have a high GOR gas layer that will deplete first because it has higher mobility, lower viscosity, and all that. And then you have a low GOR layer that depletes later. This is very, very simple to model. You just do something very similar. You just don't have a difference in perms. The same. That was a constant GOR case. Sorry about that. I'm going to do the decreasing GOR. So this is just like if you have 2 layers, that's the same perm, and then you're giving it just 2 different GORs, a very low GOR and a very high GOR. It will come up with this. Like in the reservoir, it's low GOR oil, and it's basically a dry gas. What's being produced and what's being modeled is what looked like wet gas initially, almost constant here, or lean gas condensate, and then it starts to drop like this. So that's a way to model this. I don't see too much of this in like my practice, which like we probably see tens and tens of wells every single day coming across my desk, at least just for support and these things. And I rarely see, I don't see that this often, but if you see it, at least this is a plausible explanation for it. Last thing I want you to have in your toolkit, and again, you should be able to look at the GOR and it should tell you something about the well. Here you have something that at least I use a lot. If you have GORs that as soon as you go below the saturation pressure, they kind of shoot up like this. Also, you can kind of see it here too, shoots up to another level. That typically means that there's no pressure drop between the matrix and the wellbore. So, then you have infinite conductive fractures basically. So it's very easy to model this. If you see that you're dealing with this, as you see to the right, that you have what I basically call a linearly increasing GOR, then at least I see a lot of our clients very typically in Anadarko Basin for some reason. I think there's something they call it the gummy bear stuff that they're putting into the completion practice there. So I don't know if that has anything to do with it. But that linear increasing GOR is at least extremely easy to model with only one change, and that's to reduce your fracture connectivity to a low number, and then you can model something like that. So with that, clock is 10 o'clock. We are going to, okay. Yeah, and I'm going to do the questions after the break. But there's great questions here, and we'll number 2. Yeah, I'll talk about these. Okie dokie. So we're back at it again after the break. I'm gonna just follow up on a few questions that we got from the last session. But before that, can people just like make a reaction or something if they're back? I did a clap, but okay, people are here. Excellent. Thank you so much. So Chris Turner had a good question. Are there some general ranges we could expect for API gravity depending on the initial GOR? Absolutely. But the general ranges, in general, what you should think about, Chris, is like, okay, the lower your GOR is, the lower your liquid API gravity is typically, and then as your GOR is increasing, then your liquid API gravity is typically increasing as well. What those ranges are, they would typically be a little bit basin to basin specific. That's one thing, and that's because what dictates the liquid API gravity is a lot of the properties of the heavier components. So if that's a very aromatic fluid or paraffinic fluid and emptanic fluid, those general ranges will be a little bit different from basin to basin. And in all these studies, actually, all these multi-client PVT studies, I'm pretty sure that there's like the data, like the liquid API for all the different GORs and these kind of things are provided there. So there's definitely a connection there. But the liquid API gravity, just like with GOR, is process dependent. So if you have a very complicated process and more of those lighter components goes into the oil phase, the liquid API gravity will actually go up as well. So you would, that's the thing that typically comes into play, that when people are collecting liquid API gravities, they haven't really collected liquid API gravities on a consistent basis, because they might have a GOR with some process, like say a 3-stage process, and then and an associated liquid API gravity, and then they have a GOR from another separator process with another liquid API gravity measurement. So that's why, like, when it comes to consistency of developing those relationships, that requires a little bit of care. But there's definitely a relationship there to be expected. And what you'll see in the software is that if you increase the GOR, they're like the seed feed tables that is helping you to, or that library of compositions has like an inbuilt behind the scenes, quote unquote, call it correlation or relationship between GOR and liquid API gravity. I'll try to go through all of these. All I had, can you expand on number 2, the physical reasons behind it? Was that the low fracture conductivity slide, Ale?
Yes.
Yeah. So just for everybody there.
But I asked that before the break, Matthias. If you want to go there, it's fine. If not, we can revisit later. I don't want to delay the people.
Yeah, no, I can just, so that's the large pressure loss from matrix to wellbore. Could be modeled very simply in a numerical model if you assume that your fracture conductivity is really low. Some people don't believe in that, so it could be something else. But mathematically, in terms of, or how it would look like, is on a square root of time plot, you will have a positive intercept. So either you have a wrong initial reservoir pressure, or there's something there that is creating this pressure drop in general. And I think the most common way to model that is with just a low fracture conductivity assumption, and that's what I see with most of the companies that uses that approach. That's what they at least do in the software.
Thanks.
The Adam has a really good point. Do you often see changes in facility design causing variations in fluid characterizations? For instance, when he uses public data, there's different operators that use different separating conditions, and that would also generate different GORs for the same in situ reservoir fluid. So you can see that being an issue when you map phase windows and these kind of things. And that is a really, really good point. And that's kind of a little bit related to Chris's question, again, with the liquid API gravity, that if you're not assuming the same surface process when you compare these PVT properties, you're actually not doing a consistent comparison. So that is a little bit of an issue, but that's more okay. Did you pick the right in situ GOR in general? So maybe you guys remember the slide we showed earlier, where we showed the thing from Equinor, where they've taken all the samples that they have in the whole company, and they plotted the GOR versus the C7 plus mole percent. So the composition is not like the total well stream composition is not a function of surface process. So C7 plus doesn't care about the surface process. The GUR does, but that's why there's a little asterisk here that says this is a simulated process GUR. So what he has done is that he's taken all of these compositions and then processed them through a fixed surface process such that the GUR on a like-for-like basis is consistent. But definitely, Adam, in your case, that is an uncertainty. Some rule of thumbs there is for low GUR fluids, the surface process won't be really important. So typically below 1,000 scuffs per barrel, it won't have much of an impact. And a good way to remind yourself of that is to think about all the PVT correlations. They don't input the surface process at all, actually. And they are typically valid up to 1,000 scuffs per barrel. Of course, also for a dry gas, the surface process doesn't matter. But when you go above that, then that's when it starts to become more important. So if you're dealing with a low GUR basin, then it's less of an issue than if you're dealing with something that's really liquid rich. Adam also had a question. Would you classify case study 10, page 26? Would that be indicative of infinitely conductive fracture? Page 82. That's a good question that I haven't really. So page number 66. Yeah, this would kind of be a good example of that, where it shoots up really fast. So that would be at least my interpretation without doing any more modeling work on this faults. But it allows you to just look at GUR, over time. The first thing you're looking at on the well tells you a lot of things already, just by looking at it. And that's what I would like you guys to learn as well. You can look at a GUR and it can tell you a lot of stuff downstream from your analysis. Now I've already kind of biased myself a little bit to things about this particular well. And you also see that with if you have a plateau like this, that's typically what you call an infinite acting plateau. And if you haven't read it, Steve Jones has a GUR paper. I think it's GUR paper. This guy that really goes into how GUR performance and stuff like this can be used from a well performance perspective as well. This is kind of the 101 plot. Hit saturation pressure, boom, and here it's infinitely conductive. It reaches a transient plateau where the GUR is essentially flat, just at a different level, as long as the bottom pressure is flat, which is very similar to what we're looking at here. Shoots up, boom, pretty constant, and then it starts to shoot up again later time, most likely because it's entering boundary dominated flow. But if it's a more low connectivity system, then these plateaus are basically masks, and that's what he's talking about right here. Very good, thank you. And I'm not telling you, like, your API and GUR maps, they're 100% perfect. I was talking about everyone else. So good. Next session now, it's going to be a little bit more, call it slideshow, and then in the last hour, that's when we're going to do the exercises. So remembering back to how we want to go through the course, we need to find petroleum fluids. That's what we need to do first. Once we've found them, we need to send them to the lab, etc. So some of the stuff here is meant for reference that you can keep later. What did Matthias say about fluid sampling, yada yada. So we'll go through it. But when it comes to petroleum fluids, we typically deal with alkanes, what's called paraffins, neptanes, and aromatics. And when you go to a basin, the first thing Curtis Whitson does when he gets a fluid report for a new field, it can be the biggest fields in the world, like the Gavar field in Saudi Arabia or whatever. If he hasn't done it, he goes in and he calculates what's called a Whitson characterization factor. And it's spooky because Curtis remembers all of these numbers in his head. So he just does this on a piece of paper. And he can automatically then, without doing anything else, say, is this field more paraffinic, aromatic, or something in between that's called neptanic? And this is just the molecular weight of the stock tank oil and specific gravity of the stock tank oil. You plug it into this formula, and it gives you a number between 8.5 and 13.5. And for paraffinic compounds, the number is between 12.5 and 13. For neptanic compounds, it's between 11 to 12.5. And for aromatic compounds, it's between 8.5 and 11. So there's some overlap in this number among the different families of hydrocarbons. And of course, a combination of something that's paraffinic and aromatic will pair to be naphtanic, which was what you're dealing with in between there. And that's very, very important, because as we'll talk about later in the course, when it comes to these equation state models, the properties of the heavier of the lighter components, like nitrogen, like the non-hydrocarbons, nitrogen, CO2, and H2S, and all the known hydrocarbons numbers from C1 to C6, they are known. They're like the properties are given in any chemical textbook in the world, and they're the same. Everybody knows that the C1, no matter if you're in the Bakken, Permian, Powder River, etc., the molecular weight is 16 grams per mole. That's a fact. The problem is when you're dealing with these components that are heavier than C7. So for instance, if you go to C15, C15 can have up to 1,500 isomers making up C15. So your job as an engineer is to try to find out what is the average C15 for this particular field. So that's what we've done in all of these different studies. And the thermodynamic properties of C15, or that average C15, would be very linked to whether that is a paraffinic fluid or an aromatic fluid or something in between. So that's what we call the relative paraphinicity and aromaticity. So that's why this stuff right here is really important. And you can plot just the specific gravity to molecular weight relationship, and you can get these different ranges. It's more paraffinic, it goes further down. The non-hydrocarbons is of course known, but they're always, like we know the properties of them. They're typically found in reservoir fluid. CO2 and H2S are typically unwanted and costly to deal with. Maybe CO2 now has a little bit of a better reputation. Maybe you can use it for other things. Nitrogen just reduces the heating value. So, the more we have of this stuff, the more bearish we get on that in general. In terms of how you link this to stuff that you hear about all the time, NGL, LPGs, LNGs, what's the difference? So it might be a little bit confusing, but liquefied natural gas, that's primarily liquefied methane. Liquefied petroleum gas, that's typically C3 and C4, and NGLs, that's just liquefied or natural gas liquids, that's C2, C3, C4, and C5. Crude oil, typically higher than C5. And where do you use it in your day-to-day life? Methane, we use it for heating, ethane for plastic, etc. And then your natural gas in your car, that's typically stuff that's heavier than C5. Okay, so hopefully, at least I know how to drive a car, maybe not really well, but and I have to fuel it from time to time, and I know what I'm putting into it. Great. So we found the petroleum fluids now. We know the basics. Like we classify this into aromatics, paraffinic fluid, or naphtanic. And the reason why we go into sample a fluid is, of course, to get its compositions, so we can generate the well stream composition. And we would like to also use that data to the PVT data to create an equation of state model or a PVT model. There's different types of models that we'll talk about later. When it comes to the sampling process in general, I'm not going to read this out for you, but this is going to be a reference for later. This is just some general guidelines that you can use. But just like with the fluid initialization, collect samples early at low drawdowns and stabilize GORs. That's it. And again here, remember that even though the GOR has been recombined at some non-in situ representative GOR, you can still use it. Don't throw it away. I think literally probably hundreds of millions of dollars worth of PVT data is not used because people think it's bad data just because it's not recombined at the in situ representative GOR. But it's super valuable data. So you want to have all that data in general, as long as it's not mud contaminated. Not an issue really for tight unconventionals. So a reservoir representative sample, that's any uncontaminated fluid sample. In situ representative, that's a sample that's representative of the original fluids in place. That's what we tried to do in that case study where we went through all those 20 wells. And remember, accuracy of the PVT data has nothing to do with the fact that fluid is in situ representative or not. And here is just a little bit more details on that difference between the two. When it comes to different types of samples that we many times have, we have production test sampling. We have, depending on where you are in the world, we can have many of those, and we can use it. We get stock tank APIs, etc. from that. Separated sampling costs a little bit more, but it gives you the separated oil and the separated gas that you can use also in, for instance, the Whitson Plus software. And you could actually, instead of inputting the GOR, you could go in and say, okay, I would actually like to input the separating compositions here, separated gas, separated oil, and then the software goes in and and does the recombination for you. And then you have something that is not that common in conventionals, but it is, we have samples from the Permian and from the Bakken, etc. That's what you call bottom hole sampling. So then you've already cased the hole, and it's only recommended typically for undersaturated oils when the flowing bottom hole pressure is above the saturation pressure. It's not really recommended for gas condensate and highly viscous oils. And then you have something called the open hole formation testing samples. Those are point samples in the reservoir. Those are not really used in tight conventionals, but they're used offshore and whatnot, because they require a certain permeability. And they can actually be used for most type of samples as well. But again, this is more for reference, so you have it for later. But they will give you an exact point composition of in this place in the XYZ space. You'll get a composition with the open hole formation testing sample. Okay, and this is just a quick summary of the different sampling procedures. But typically, 99% of the samples that we're dealing with in tight conventionals for PVT work, that is so-called separated samples, and we recombine them in the lab at whatever GOR we tell them to recombine it at. Whether that's in situ representative GOR or not, you can still use that report as long as the PVT data is good. So once the laboratory has gotten the sample, they put it into what's called a PVT report. And maybe some of you have worked tons with PVT reports, and I know some of you have, and maybe some of you have never touched a PVT report in your life. So I'm going to give you kind of the PVT report 101. So again, if you want all the details, we have this course next week. But these are the things that I think it's important for, even if you're never going to look at a PVT report, you should just know the basics of a PVT report. So that's kind of, I call it a crash course for PVT report. So we're going to go through, like, how does a PVT report actually look like? That's one thing we're going to do. We're going to try to understand what typical lab experiments are we dealing with, and what do they measure. And then we're going to actually emphasize that most of the data in the PVT report is not measured. We're going to talk about compositions, which is one of the most uncertain lab experiments. And then we're going to talk about liquid API gravity, the fact that that's defined at stock tank conditions. And then we're going to realize in the end that we actually don't ever put a PVT report into a simulator. We always have to go through a model. Either that's a correlation, a PVT table, or an equation of state. So in the handouts that was given to everyone, we in the digital material that was sent in the email, there is a PVT report example. It's from the Duvernay. That's why we can use it, because it's up in Canada. It's public, and it was collected by Encana, and it's a good example of a PVT report, how it looks like. In the PVT report, these are typically could be hundreds of pages long, and this is just an example of a PVT report. Huge report. And if you want to find something just as trivial as the formation volume factor, you'll realize that you need to look many places to try to find it, and you need to also look know what you're looking for to be able to find something as, call it, standard as the formation volume factor. So I thought we could maybe do that in the end of this. So first of all, this is how a PVT report looks like. It has typically a lot of information in it. Most of it, as we will talk about in a sec, is not measured, but it's calculated. Before we go there, we're going to talk about, like, what are the basic things that we measure in a PVT report. On a broad basis, it's some compositional measurements, and then we have a bunch of standard PVT experiments. And then if you want to go very, very complicated, we also have gas EOR experiments that is more exotic. And more used to study gas EOR processes. So if we start with the compositional measurements, there's two different options that we can do. This so-called GC measurement. That's the most standard way of measuring a composition. But here is very important to emphasize that we're actually measuring the weight percent of the individual fractions, and not the moles. But we need the moles. We'll talk about that. Then we have the true boiling point distillation, which is actually never really done in practice unless you ask for it. I know some of the people on the call have done that in the different studies. We've done that in Anadarko Basin, Permian, Montney, etc. And that actually gives you the weight percent, the molecular weight, and the specific gravity of each individual fraction. So you can actually take those guys, convert them back to moles, and then plug that into your model. The CCE gives you gives you a lot of different things, but it primarily, that's where you get your saturation pressure and saturation pressure type. So this is where you get, so this is called the constant composition expansion experiment, sometimes also called the constant mass experiment, and or constant mass expansion, and that's where you get your P set. And then you have the depletion tests. That will be, for instance, a so-called DLE or a CVD, and that's tests where you actually remove mass from the PVT cell, and you get actually compositional variations with each stage. And that's where you, for instance, get liquid relative volume curves, shrinkage curves, dropout curves, etc., which you actually can now get in modern CC cells too. Then you have your multi-stage separator test, which gives you your BO. You have the viscosity experiment, which will give you the viscosity of the oil. The viscosity of gas is actually almost never measured. Curtis can probably mention if he has seen many, but I think we can probably count on a couple of hands how many actual reservoir gas viscosity experiments we've ever seen. So typically that's because gas viscosities are easier to calculate. We have the slim tube experiment for gas EOR that gives you the MMP by multi-contact. Swelling test gives you the MMP by first contact. And then we have an experiment called multi-contact vaporization that gives you the vaporization efficiency. So on a broad level, that's what this suite, that's kind of the pretty full suite of the different experiments that you're dealing with, where most of the common ones would be the GC to get your compositions, CCE to get your saturation pressure. For oils, you will have typically these two ones as well, and you would have one of these depending. Typically, a DLE is for oil and a CVD is for gas condensate. So that's on a broad level what the experiments are and what they kind of give us in a little bit layman's terms. And there's a couple of slides here that's meant for reference, just on the uncertainty of the different experiments. And these are just meant for reference that you can keep for later. But just note that oil viscosities is one of the things that's typically the most hard to both model, and is also has probably one of the largest uncertainties of all the laboratory measured quantities together with composition. Then I have this slide right here, which is just showing the compositions, so the mole and mass fraction of the PVT report that I provided you guys. So it has and this is the recombined reservoir fluid. And I would like you to take I'll give you 20 seconds. Just look at this particular screen right here. Maybe I can zoom in a little bit, but it has component name here, and it has the mole fraction here, and the mass fraction here, and a few properties over here to the right. And I would like you to think about, on this page, what is actually measured and what is actually calculated, and what you get from a PVT report. So I'll give you guys, what on this slide is calculated and what is measured, actually rawly measured. And I'll give you the answer, and that might be kind of surprising for many of you. So this is the reservoir fluid composition, and a lot of people goes here directly and they take this mole fraction right here and plug it into a model. And I can tell you, on this particular page, there is nothing that is directly measured. Of course, the calculated properties here to the right, obviously calculated. The mass fraction here is actually not a direct measurement of that. We'll talk about how that's actually done. Again, just to emphasize that most of the stuff in the PVT reports are actually not measured. A lot of it is calculated. So how is a recombined reservoir fluid actually, quote unquote, measured? Well, that's what we're going to try to show here at this slide. So if you measure separator fluids, you have a separator gas and you have a separator oil. First, to estimate what the separator oil composition is, you need to flash that down to stock tank, and you'll get a stock tank, a flashed gas and a flashed oil composition. And you put this into the GC, and these are actually the two only things that you measure this flashed gas composition and this flashed oil composition, and then you recombine that at whatever the solution GOR of the separator oil is to get an estimate of what that composition is. Here, you're measuring the weight fractions, and you have to assume a set of molecular weights to convert them to mole fractions. And with that, you're getting the separator composition of oil. This one you can put straight into a GC and get a composition. So this guy is measured, this guy is measured, and this guy is measured. Then you take this, which is calculated, and this that is measured. So it's calculated from these properties here, and you recombine them to a reservoir fluid composition. And then sometimes you actually take this reservoir fluid composition and you flash it. This is a quality test that the labs are doing, back to stock tank conditions at a certain GOR. Oh, you get a certain GOR and you can recombine it, call it again. So you do a recombination this way and a recombination this way to see if these are similar or different. And many times when you do that and you ask the lab for both of these, you'll see that the uncertainty in, for instance, C1 or molecular weight of C1 can be up to 2 mol%. So again, speaking to that, these compositions that we're dealing with, they have a big uncertainty, and we don't. Some people think that you just take a reservoir fluid composition and you magically put it into a PVT cell and you measure its composition. But it's actually these end products right here that you're actually measuring, and you're measuring their weight percentage. That's what's actually being measured. Convert them into moles, and then you have to do the recombination to come into this reservoir fluid composition. And this is the formula of how you do it. When you look at the petroleum system components, you know that the non-hydrocarbons and also the pure compounds with known molecular weight that I talked about already, the properties of those are known. Then we have something called single carbon number components, which, for instance, can be C10, C11, C12, etc. They're always estimated. And just for reference, if people are working conventional reservoirs, you have that there as well. And in this table to the right, you'll see, okay, these are the non-hydrocarbons and these are the pure components. So everything like the molecular weights for these are known. And then we have a mix of isomers and single carbon number components. And then we have the single carbon number components. And they are actually, the molecular weight there is just estimated. And these are what we call cat spheres of body molecular weights. So if you go into a compositional measurement per se, or a compositional recombination, the GC tool is actually just measuring the mass of the individual components. Okay, that's what you're getting from the GC tool. And then these weight fractions are converted from weight fractions to moles by using the following formula right here. So this thing is what's being measured. This thing is also measured, but it actually has an uncertainty of plus minus 5 to 10%. And then this guy is known if you're dealing with a pure component, and it's estimated if you're dealing with a single carbon number component. And in the table to the right, you're seeing exactly, this is just from a Schlumberger report, and they report the CAT's spheres of body molecular weight. And Curtis also wrote a paper. Maybe if Curtis is, are you here, Curtis, now? Yeah, if Curtis was here, at least he could explain the story. But it's basically another set of molecular weights that's matched to this particular set of data right here. And it's just two quote unquote arbitrary molecular weights that's being used in these laboratory reports. And these are known up to here, and then these are estimated, and they need to be estimated for every single base. Okay, so main point here is that compositions are very uncertain. Probably one of the more uncertain things that goes into at least of the laboratory experiments, and that's something that should be good for you to know about. One thing we see many times is that API gravity is being used for conditions that are not stock tank conditions, and just this is a good example of that, where they're using this is the hydrocarbon liquid analysis at separated conditions. So the separated conditions are the separated conditions are not stock tank conditions, and the API gravity, that number, is defined at stock tank conditions. So they have basically measured the density of a separated fluid and just converted it with this formula to an API number, which doesn't make sense, because when you flash this thing to stock tank conditions, some gas is coming out of the system, and you're now dealing with a different composition. So just make sure that you always are aware that the liquid API gravity is a stock tank condition type of metric. And the last thing, just to emphasize that, is that we never put a PVT report into any simulator or to any exercise. It always has to go the step between a model to the simulators, whether that's a correlation table or an equation of state. And that's what we're going to talk about next here. Yeah, and what was mentioned here by Tarun is absolutely correct. So that mass fraction is measured and mole fraction is calculated. Excellent. Good. So now we're going to talk about these PVT models, and there's two different types of PVT models. It's the so-called equation of state model, and it's the Blackwell table. So we're going to go through both of those. And an equation of state model, we introduced that earlier. If you want to understand what it is, we can go back to the fundamentals. If you think about a tank model where a particle exhibits a basically a force on the tank wall, and you take that force and divide it by area, that's the definition of pressure. If you have a bunch of these molecules running around in the, or I don't know, flowing around in the tank or whatever the word is, there will be a base pressure on the tank. If we increase the temperature, or if we double the speed of these particles, which is basically what it is, you will hit the tank size wall more often. Pressure is increasing, temperature is increasing. If you double the number of particles, the number of particles, if you double them, you'll hit the wall more often. Again, pressure is going up. And if you increase the tank volume that we're looking at right here, then the opposite is happening. Your pressure will start to go down. And just with this very simple tank model, we've been able to make a few observations that pressure is proportional to temperature, pressure is proportional to the number of moles, pressure is inversely proportional to volume, and that results in what we call the ideal gas law. And the ideal gas law was introduced almost 200 years ago, and it's one of the most fundamental versions of an equation of state. Then a few years later, this guy called van der Waals introduced a so-called cubic equation of state. And what we're dealing with in the oil and gas industry, primarily 99.9% of the time, is these equations of state that becoming industry standards in the 70s. The SRK equation of state and the so-called Peng-Robinson equation of state. Both of them are cubic. They have a very similar. I don't think you can say that one of the equations are better than another. I think you can probably even convert from one equation to another. So they're very, very similar. Why do we have two? Really good question. I think there's just a historical answer to that SRK became really popular in the process community, and then Peng-Robinson became really popular in the reservoir community. And at some point, we started to kind of bridge models where you had the process models and the reservoir models start to work together. And now in most of the industry packages, we have both of them. But again, to use an equation of state, you need to have pressure, temperature, and composition. That is what predicts the PVT tables. How does an equation of state look like? If Curtis wanted to send me an equation of state, he would basically send me either the Peng-Robinson or SRK equation of state. It will have two tables, the component properties and the binary interaction coefficients. So that's how it looks like, and there's different industry standard formats. Typically, Eclipse 300 is an industry standard. And then what we've done in all of these different unconventional basins is to take all the PVT data in the basin from all the different well locations in all kinds of different formats from all the different labs, because all the labs have different calibration techniques and whatnot. And we created one field-wide equation of state that you can then use as a tool to predict PVT properties really, really, really accurately on every single well you have, even without much PVT data. You could, for instance, just use something as little as the GOR that we went through in the exercise earlier today. This is what we call a multi-sample equation of state, where the definition is that each sample is described by the same equation of state model, where each sample's unique composition is all that's required to accurately predict PVT data for that specific fluid. And then, of course, the great question is like, okay, why do we then need a different equation of state for the different basins? That's what we talked about earlier, that some basins are more paraffinic, some basins are more aromatic. We might have something in between. So these heavier components and how we define them, that's the difference between Bakken, Eagle Ford, Niobrara, Powder River, or whatever. And it's also the reason why we can't just create one equation of state for every single basin in the world. So once we have an equation of state, we need to be able to predict the compositions, because that's an important input. And how do we really get compositions? Well, one way of doing it is to go to the lab and measure the composition in the lab. That is a viable solution. Typically costs a lot of money, especially if you start to store it and whatnot. And we also already looked at the PVT report example, and you could see in that PVT report there was little hundreds and hundreds of pages with compositions, and finding the right composition to use is sometimes tricky. So that's why typically less than 1% of the wells in the basin have these recombined well stream compositions measured for them. So what do we do with the 99% of the other wells? And that's basically what I'm going to show, here real quick. We just use readily available data. And in the software, there's different methods that we're going to go ahead and apply it later after the break here, depending on what data you have available. But I can use the same equation of state. We actually saw that earlier. We went across all these different fields, and I could take, a 10,000 scuffs per barrel fluid, which would be, adding a 10,000 scuffs per barrel to this guy. Now I'll be dealing with a gas condensate fluid, 1,000%. All the points here are red, and my reservoir classification is gas condensate. This is my dew point. And above the saturation pressure, I'm dealing with only reservoir gas. Then if I had other types of information, and I had, for instance, let's say I had a GUR and an API number, I could go in and say, okay, I have 600 scuffs per barrel in terms of GUR, and my liquid API gravity is 38. So I can add more data if I have more data available. What's important with the liquid API gravity, back to Adam's point earlier, is that if you're using a process that's not consistent with the GUR and API number, that makes you, typically that can get your numbers to become a little bit off sometimes. So that's why I actually, in general, have had more success with just using the GUR method. So I don't trick myself into thinking that having the liquid API number there is more accurate, because most of the times there's been so many steps and so much potential knowledge contamination going from the actual measurement of the liquid API gravity before I put it into the model. If you have, for instance, separated GURs available, that you don't have anything else separated GURs, you could go in and input the separated GUR too. That would mean that, okay, this is 1250 scuffs per barrel at separated conditions. I can even associate a process to this or a condition to this time step. Or in this case, I'm just assuming it's 100 or the same as my surface process. And if I also want to use the GUR saturation pressure method, I'm saying, okay, I would like to use the separated GUR, and I would like to match a saturation pressure of 3,000. Why do I then have and that's basically this guy right here. So why would I, know or think I know the saturation pressure of the fluid? Well, if you have a GUR profile like we looked at earlier, I think Adam talked about a really good example of that, which was the one in was it 64, I believe, or was it 66? This guy. So at a constant GUR, then it rises. Okay, if I've calculated my bottom hole pressure at the same time, and I see what my bottom hole pressure is at the same time when this starts to shoot up, I can basically provide a field indication of what the saturation pressure is for this particular fluid. And that's how I can use this method, such that when I go to the PVT now, my bubble point is exactly 3,000. And then you will see that my total GUR is not 1,250 because I've inputted a separated GUR. And from separated to stock tank, there's a shrinkage that should make the GUR here larger than what we're dealing with before. Okay, so the main point here is that you can use whatever data you have available to initialize the fluid, even though you have or are using an equation of state. But then there are some methodologies in the software that will help you predict those different compositions. So when we looked at these examples right here, we'll see, okay, this is the fluid composition that's being predicted in this case. And if I also show you just an example of, okay, if I have a dry or wet gas composition, okay, I could either use the so-called fluid composition method, and then I can just input those values directly. As that can be like 80, it can be 15, and 5, I think was the numbers, like this. Click save. This would obviously be a dry gas. No two-phase envelope, and this is my dry gas table. but I could also go in and use the dry and wet gas composition here. Can input a specific gravity, 0.6, let's say, or I could also go in and actually specify, which is very typical, where you go in here and you say, okay, for the dry wet gas composition, I have compositions up to C6. Then you need to assume some kind of molecular weight too. It's a very common data set, and you can do the same exercise. You can do like 15 and 5, for instance, something like this, and it will give you the same results. So that's just using the available data that you have to predict the composition. It's really powerful. So if you think about, in the software, we create these tables, and the tables is what we really are using in the day-to-day engineering. So when it comes to the actual black oil PVT tables that or the black oil PVT model that we're using, it's important to understand where it's coming from. So if you think about the PVT properties in general, pressure and temperature and composition, that is what how this, the inputs to the model. Super complicated space. It has 2 plus n minus 1 dimensions, where n is the number of components. So if you have 50 components, you probably have thousands of components really in these fluids. It's impossible to visualize. But the nice thing is, if we simplify our world into components of 2, then we're dealing with what we call the black oil model. And here it's important to understand that the black oil model can be used for all reservoir fluid systems, not only for black oils. And the reason why it's called black oils is just because it's a tradition that when it was introduced, it was a 2-component PVT model. It was introduced a long time ago, where the oil in the tank was always black, and the other component was the surface gas. But probably a much better way to talk about this model is to refer to as that just a 2-component PVT model. But right now we're kind of I think that train has been that train has left the station for sure for a long time ago. So we're just referring to it as the black oil model. And the black oil PVT model has 2 components. It's the surface oil and the surface gas component. It has 3 model parameters for each phase: the formation volume factor, the RS, the viscosity. And on the gas side, it has similar properties. So the formation volume factor for gas, the solution CGR, as we talked about, and the viscosity. And instead of using compositions, you're using the solution GUR or the solution CGR, scaling that up and down to see how rich or lean that fluid is. And that model is dependent on surface process. So here again, we're going to take a 10-minute break from 11 to 11:10. Then we're going to finish up with a little bit of theory after the break, and then we're going to just do some very simple, hopefully, exercises in the software to make sure everybody has at least run some of this. And then we're done in around an hour. Goody. So just as people are getting back to their seats and stuff, so there was a couple of questions. One is really good from Lindsay. If are there basins that need multiple equations of state to accurately represent changes across the field? And that was like when we started to do this, I think the first basin was the Eagle Ford. That was kind of one of the big uncertainties. Would this even be possible to create one equation of state for the whole field? And at least for all the unconventional basins we've been looking at, which is probably 14, 15 basins now, we've been able to successfully create one equation of state for those basins, which means just that the relative aromaticity and perfluenicity in the basin itself is really consistent, even though the compositions are changing drastically. But there has been cases in the past where I know Kurz has been working. I think there's like offshore fields in Indonesia and stuff like this that have different. Can't remember, it was like a aromatic oil rim and then a perfinic gas cap or something along those lines, where you would have to do some special tricks to make sure that you can accommodate for those changes, Lindsay. But the findings, at least from conventionals, is that it hasn't been needed. And then Adam is asking about if you can capture changes to separated conditions over time within the software, and the answer to that is yes. And also for your case, where let's say you change from a 3-stage separated process to a 2-stage later in time, we can also talk about that, but maybe just offline. But that's basically common process conversion in the software, which is just a click of a button does that for you if you're in that situation. Good. So we were talking about black oil PVT models, and I have around 19 minutes to before we're going to go into the exercises. I'm promising you this is kind of a little bit of a special course because it's more theory than necessarily clicking the buttons and stuff, and that's more heavy in the other courses. But what we're going to do in the exercises is we're going to use some real field data, and we're going to initialize a oil well and a dry gas well, and we're going to do some simple exercises with that. So we were at the black oil PVT model, and to understand what a black oil PVT model is, we need to define some definition of what's a reservoir oil and what's a surface oil and gas, etc. So when it comes to a reservoir oil, we use this is SP nomenclature. So reservoir oil, then we have VO, and if it's surface oil originating from reservoir oil, we denote that O hat G, and then if it's surface gas originating from the reservoir oil, we denote that as VG hat O. For a gas reservoir, it's the opposite. We have reservoir gas would be VG, surface oil from the reservoir gas phase is VO hat G, and then the surface gas originating from the reservoir gas is VG hat G. Okay, and why that makes sense and why you need to have a distinction between the two is if you're producing below the saturation pressure, you have two phases in the reservoir. It looks like this. You would essentially produce, some gas at surface originating from the gas phase and some that's originating from the oil phase. And that's why these PVT properties becomes especially important as you are basically dealing with free gas flow and free oil flow. So these are the different surface products that you're dealing with, where the second part, this is a surface gas, but it's originating from the reservoir gas phase and vice versa. That's what's being used to define the PVT properties. So where the dry gas formation volume factor is this guy, and the solution CGR is this guy right here. So to go through it, the dry formation volume factor is the reservoir gas phase divided by the surface gas originating from the reservoir gas phase. And then the solution CGR is just surface oil originating from the reservoir gas divided by the surface gas originating from the reservoir gas. While on the oil side, it's the opposite. So you have the formation volume factor for oil is the reservoir oil divided by the surface oil originating from the reservoir oil. And the solution GOR is the surface gas originating from reservoir oil divided by the surface oil originating from the reservoir oil. So you need to see that those are different. These properties are process dependent, which means that if I changed the process in the software, if I went in here and I had a GOR of 1,000 and I calculated the formation volume factor, I'll have formation volume factor, let's say in this case, low GOR fluid, then I'll have a formation volume factor of 1.46. But let's say I change the process, exactly the same reservoir fluid. If I take this reservoir fluid in, and I just say, okay, I would like to use, just need to keep the composition the same. Same thing flowing from the reservoir. And let's say I go in here and actually reduce a stage. I make this either a single stage or a two-stage. So I can go in here and remove a stage. This becomes less efficient, and I can recalculate this. And then we can see, okay, is my formation volume factor going to go up or is it going to go down? So I went from a two-stage to a single stage. It's a less efficient process, and I was at 1.46, and I should probably go up to a number that's higher than 1.5. So you see, it has exactly the same fluid, but the only thing I changed is the process. What you probably didn't notice is that the viscosity is the same. So the viscosity terms are process independent, process independent. The oil formation volume factor looks like this. As you're undersaturated, the only thing that happens is that you're getting a denser and denser fluid. As you hit the saturation pressure here, the bubble point, the oil formation volume factor is decreased. Solution GOR is constant above the saturation pressure, and then it's being reduced as you're in the saturated region. The gas formation volume factor also has a saturated and undersaturated part. It hasn't that big break at the dew point. When you took Curtis's class back in university, I remember that for this plot, you were a B student or worse if you plotted the gas formation volume factor like this. And the A students, they would plot the inverse because it's much easier to read. So let's say I want to read something here, and that inverse is what you call the gas expansion factor. Much easier to read at values that's relevant over here. But you see there's not a big change for most fluids as you are going from saturated to unsaturated, where the dew point is here. The composition will be really different though. That's right here. And again, this is what you will see in Whitson +2. It will monotonically decrease, and then it will be a non-monotonic, or that the shape will turn, and you get this kind of hook, or whatever you call it, at lower pressures. So this is, this is probably 1,000, and then this is probably 750, etc. To explain this, you need to know what K values are. We've already talked about that 3 times. Or 2 times, but we'll repeat it again. It's just a relative preference for a component to be in the gas phase or to be in the oil phase. So the relative preference for a component to be in the gas phase, so the K value is larger than 1, etc. So just to give you the basics here, at low pressures, the K values are behaving linearly on a log plot. Okay, so this, the slope here is basically -1. And at low pressures, what is that? Around, let's call it less than 1,500 psi. And then above that, that's when the K values start to behave very complicated, or complicated behavior. And that's what Curtis usually talks about, the shape of the nose here. That my nose and Ali's nose, and like we have different shapes of our nose, and it's exactly the same thing with the different reservoir fluids, most of different basins, and that higher pressure region is really complicated and to model. And all of these different K values for the different components, they converge at something called a convergence pressure, and that's where the K value for all the components is 1. And this part is really, really complicated to model, so you need an equation of state to be able to capture this complexity, this non-monotonic behavior for all the individual components, and also the sum of how that works together. That's the general shape of the K values. And the heavier K values, which you see here, they'll start to turn on some low point before they start to go up. And that's the explanation to what we're seeing both in the laboratory reports. There was a question from Tarun earlier about it as well, and also why the RV curve or the RS curve has a condensation-driven period and then a vaporization-driven period. And that's because these heavier, the K values of these heavier components, they are non-monotonic. At some higher pressure, they like to be in the gas phase or in the oil phase, and then that switches. So it switches from a net condensation-driven process to a net vaporization-driven process, and that's why you see this particular shape right here. And then you can ask, why but why does like the K values of C30 plus behave like this? What's the physical reason for it? And if you think about it, that's kind of like it's the same as asking, why does water boil at 100 degrees C at atmospheric conditions? I don't know. Like it's a physical property of that component, and it's a little bit the same way you can think about this. It was given to us by Mother Earth. Great. So if we bring in these things that we learned here in terms of in place volumes, we've learned all the time that getting the oil in place numbers, it's the hydrocarbon pore volume divided by the formation volume factor for oils. And if you want a gas in place numbers, you just take that number and you multiply with the RS term. Similarly, on the gas side, you can use a similar formula. You take the hydrocarbon pore volume divided by the formation volume factor, and then you have to multiply. That's how you get the gas in place number. And then to get the oil in place number, you need to multiply that gas in place number with the RV term. So that's one way of doing it. One way I like to do it, and what we teach in this class, is to use something called the total formation volume factor and the total GOR. That's something that the software reports out directly. It's this number right here. And you can use essentially the same formula for all kinds of fluid systems. So no matter if you're dealing with a wet gas, a gas condensate, an air critical fluid, an oil, a volatile oil, black oil, etc., you can use this formula right here. And it's just hydrocarbon pore volume, and you divide by the total formation volume factor. And then on the gas side, you take the original oil in place and you multiply with what's called the total GOR. And the general formulas, this is just straight out of Curtis's book, and it's also how it's calculated in the software. The formation volume factor, the total formation volume factor, is just a saturation weighted formation volume factor. So for a single phase oil, which means, okay, we're 100% oil saturation, that will simplify to formation volume factor is equal to BO. And for a single phase gas, you'll deal with basically 100% gas saturation. So you will get this BGD divided by RS term. The units of that is barrels per, or is reservoir barrels per stock tank barrels. So exactly the same units as the formation volume factor. And then if you have two-phase saturated case, you'll deal with some kind of saturation weighted average of the two. So in this case, now I'm above the saturation pressure. And now I'm dealing with, I have the formation volume factor is equal to the oil formation volume factor because it's 100% oil. But let's say I, in this case, changed my initial reservoir conditions to be just a lower reservoir pressure. So now I'm down inside of the two-phase envelope from day one, and then in my PVT table, I now have a formation volume factor of the oil zone and a formation volume factor or expansion factor for the gas zone. But the total formation volume factor that I can be using then in this calculation is provided here at the top for me, already calculated. So I'll just plug those guys into this formula, and I'll be able to calculate the original oil in place and the original gas in place. So using this total formation volume factor, and very, very similar with the total GOR. And then typically here, now we're a little bit on crunch on time, so I'm going to skip it. But if you want to do it, and also if you're watching the recording, you can take this exercise right here, where we have three different cases. We have an oil scenario, we have a gas scenario, and a two-phase scenario, where in all cases, the hydrocarbon pore volume is 5 million reservoir barrels. And these are three different reservoirs. And I would like you to, if you're watching the recording, if you want to do this later, you can just go in here and say, okay, I would like to calculate the oil in place and gas in place by using this trick that I basically taught you now, that you can use the same formula for oil in place and gas in place calculations. And if you go in and do this, you'll actually see that you're getting the following numbers right here. And it's very similar. It's the same formula in every single case. And you'll be just using this total formation volume factor number and the total GOR. Perfect. Okay, so now I'm going to do what I promised everyone, and I see maybe there's some questions here. Yeah, so there was a question from Mike. Is there any material available to understand what basins and phase windows were used in developing the EOS model, along with the associated constraints? So that's a good question. So the equation of state model that we're using in the courses today. So that's what we're going to do now. We're going to go into this domain right here, hopefully where everybody is at. And all of us, we're going to go into the PVT field right here, and we're going to create our own little project. Okay, so there's a field here at the top that's called PVT in Whitson Plus. That's what we're going to click, and then we're going to go ahead and add a project. And here I would like all of you guys to add a project that just make it your first name. I'll call it Matthias, and then you can call it whatever else you want, but I'll call it Matthias PVT course, something like this. This would be a private project. On courses, we're just using what's called a default equation of state, and that's just a default Peng-Robinson equation of state that is kind of vanilla. It's not tuned to any data, etc. So that's what's going on at courses.whitson.com. When it comes to the basins where you are working in general, so let's say you're working for a company and you've participated in these studies, of course, in the deliverable to each of these studies that we have on the web page in general, they are here. So all these studies right here, they'll have dedicated information and deliverables associated with them. Okay, so that's something that if you want to know it for the Bakken, for instance, just send me an email and I'll make sure to send you all that information with your data, all the data that was included in the study, etc. So they will be different for the Bakken, it will be different for the Anadarko Basin, etc. Okay, maybe I had that number already. Okay. Okay, so we're going to go and create a PVT course project. I had a project here already, a TS course. I guess. So we're going to do this a little bit slow together. Were people able to create a project? Yeah, hopefully that worked. And
I got the same error that yours showed, unable to create a project. I don't know if I'm the only one or.
Yeah, I think
I'm
maybe
also getting it just says something is wrong and not creating a project.
Yeah, okay.
Now I see it. It looks like it gave me that error, but after a little time, now it's popping up in all projects.
Yeah, that's great. Just it's probably because we all did it at the same time or something like this. Okay, but what we're going to go ahead and do now is we're going to take some data from the manual, and we're going to do 3 wells together, and those 3 wells are provided in the link that I'm going to send you guys, and it's going to have 1 oil well, and it's going to have a gas well. Let's see here. Yeah. So in the chat on Teams now, I will send a little link. So in the link there, just if you click that button, you don't have to open the data or the screen or anything. That's the only thing we need to do. And I'm a little bit unsure what. So did everybody see this the link down to the right here? Yeah, perfect. Has people been able to download that link, the data?
Mine has been flashing verifying link for at least a minute.
Verifying link? Or
that's what it says.
Okay.
Mine's still doing that, but it downloaded I had to click up in my downloads and the file was there. I got the same thing, but in the recent download history, it had the file even with that verified link up. Okay,
so that's probably just probably a security thing on your local end there. Okay. Good. So when you have the data, with that, we're going to just take a couple of those wells in, and we're going to do some initialization on both of them just to make sure you've done it once. But good. So inside of the software, it look like this, and then up to the right, you'll click Mass Upload, and then you just click here, and then you find that file on your computer, and then once you've done that, you just click Save down to the right. And I've done that already for these 3 wells. I'll show that one more time. When you're inside the project, click Mass Upload up to the right. Then you find a file and you click Save, and you should have 3 wells now. Okay? People all having 3 wells? Yeah, people have tried drag and drop. The company security does not allow uploading any workaround. Tarun, I can do it for you probably here. Just give me one second. Tarun, I can do it for you. Just what did you call your project?
Just Tarun PVT course. Any one of those 2 is fine. I had to create 2, but you don't see it?
There's so many projects. Just give me one second here.
Okay, sure.
Can you can at least try the drag and drop option, Tarun, just to have it?
Okay, so mass upload and then just drag and drop.
Yeah.
Okay. No, this thing's too smart.
Yeah, and that must be probably something on your end, I guess.
Yeah, it's on our end. Yeah, we've gone
Yeah.
ballistic with our security measures.
It's interesting that it's even like that on that domain. Okay. The
Never
fact
mind, that's okay. I'll just look and follow.
Yeah, that sounds good. We'll go ahead and do that then. So the first thing we're going to do, we're going to make it very simple. We're going to go to the well called kite at the top, and we're going to go in and which is the first well, and we're going to click PVT. Okay, and in the PVT feature, we're going to open the reservoir fluid composition card by clicking this button up to the right here, and then we're going to drag and drop this line as we like, the gray line. You can drag and drop it on the screen, or you can also input a number here. That's, for instance, 750. So to show this, we open it here. The data shows up. You can drag and drop this line as you like. I picked 750. That was a good number. And then you click save, and you'll see that the software is predicting a fluid composition for you, automatically creating these tables. And again, behind the scenes, that's this equation state model that's being used. Very good. The thing that I want you to do is to click this button right here called View Fluid Composition. That's how you will see the compositions. What you'll see for your particular well is you can take this and copy that data into Excel by clicking this button if you want to do that. The one thing you'll see is that this data has no non-hydrocarbons. So if you so that's the components that are lighter than or not lighter, but the components that's H2S, CO2, and nitrogen. So we would like to set some of those components together now, these non-hydrocarbons. So if you've participated in any of the basins and you use Whitson with those, you'll see that at least the field-wide averages will be what you get up here at default and not zeros. But what we would like to do now, so this is how you view the composition. Click this button, view the composition. We realize, okay, these are 0. So if you want to set those, you go back in here and you see, okay, I would like to set the non-hydrocarbon compositions. And then we can make that 0.5, 0.7, and then I think we can, was it 1 we had here? I'll just keep it 0, the last one. And then we can rerun the calculation. And when you rerun the calculation now, and you open the reservoir fluid composition, you see that your reservoir fluid composition will also honor whatever that content was that you inputted. And we did 0.5, 0.7, and 0. So that's how you set the non-hydrocarbon compositions in the software. I'm going to do this slow because we're doing, I don't know if this, Ulke has a question.
Yeah, so for those components, since they do come with your PVT data, if we don't have that readily available, is that something that you guys do have, or would we have to put those in?
Yeah, that's a great question. So if I did this exact exercise in on maybe I can just show that real quick. So this is on courses. If I did the same exercise in the Bakken, for instance, or in the Permian, the defaults will be what is the field-wide defaults. So that would be better than not having anything, and it would probably be the best you could do if you didn't have anything. If you didn't have anything else. So in this particular example, if I did the same exercise in the Bakken for a well that I have right here, then this guy right here, and I looked at the same values and I haven't set anything, the nitrogen and CO2 data points that are provided by default, they will be dedicated to that and derived for that basin. So they will not be horrendously off, if you like. So that will be how it's done in all the basins where we've done work. So for BPX, that will be Permian, and Eagle Ford, they will have some defaults. If you want to make it more accurate to input those numbers, where you could get them from, it's just you could probably look at your sales gas compositions, and typically they will have information about those components, and they're so light that they will always be in the gas stream and not in the oil stream.
Thank you.
Yeah, 100%. Good. The next thing we're going to do is so that's setting the non-hydrocarbons and UCU compositions. If you want to look at the saturation pressure, one way of doing that is, of course, you could look at the phase envelope here and you could kind of like eyeball it. Okay, it doesn't really work well. But the summary of kind of the fluid properties at initial reservoir conditions is here. And your bubble point for your saturation pressure is this number that you're looking at right here. This is the oil viscosity at initial conditions, solution GOR, reservoir density, oil formation volume factor, etc. Okay, the saturation pressure now 2,900. But I talked to someone that did work on this well, and they're absolutely convinced that the GOR is 750, but the bubble point is 3,000. So what we're going to do now is we're going to go back to the fluid definition, and we're going to change the method to this method right here, where we're going to input a GOR and a saturation pressure by force. Okay, so the saturation pressure should be 3,000, and then we leave the initial GOR, and I click save. That is a little bit more of a computationally expensive exercise. It requires a lot of iterations to do that exercise, but it's neat in the sense that if you have looked at your bottom hole pressures when they're actually increasing, and you see that that's around 3,000 or whatever, it can be a really good way to make sure that there's agreement between your PV or between call it your well performance data and what you're actually observing in the field. Okay, so in this case, when I've done it, I go to PVT table. You'll see that my bubble point is perfect here, and the total GOR is 750, which you see is still the same. The composition will be a little bit different from what we had earlier, and there's also a new functionality now that was requested by Pioneer. That is this button to just plot this with GOR versus bottom hole pressure. What's neat about that is that you see the bottom hole pressure here, and you see the GOR. So maybe actually for this fluid, it looks like the GOR starts to shoot up around, 2,600, 500 or something like this. So instead of actually taking the bottom hole pressure up, should actually probably have taken it down, so that you can move these lines around as well if you like to. But let's just keep this as for now. We had 3,000. And then we had 750, and I'm going to X this out. I'm also going to just monitor if there's, yeah. Okay, so now we're going to do something that's fun, and which is a really good exercise for you if you want to sanity check your the relative ratios of your decline curve analyses, and that's to go in, or we're going to do one thing first. Sorry about that. The first thing we're going to do now is to go down to simulated PVT study, which is down here in on the well test on the virtual PVT lab, and it's called simulated PVT study, which is down here, and click generate study. And what that basically does is that it says, okay, I didn't have PVT data here, but I could generate something that's equivalent to a PVT study synthetically with this composition and with the equation of state. And here you basically get an equivalent of a full-blown PVT report. You have the CC experiment, you have the DLE, CVD, viscosity experiment, etc. And you could actually even go and export this into a file that looks very similar to a actual PVT report. It's called a synthetic simulated PVT report generated in Whitson Plus. But it can be helpful to communicate with, we know, like non-op owners and stuff like this, very helpful to communicate, with these documents. You can convert it directly to a PDF if you like to, with the click of a button here. So that's a neat feature that a lot of people like to use. So when we look at this, what kind of fluid do we think it is? That will be my question to all of you guys, and please answer in the chat, I guess, if you have anything. Okay, black oil, excellent. Okay, I think that's a black oil too, so that's good. If it was more of a volatile oil, you would probably see in some of, it's very linearly decreasing liquid dropout curves here. So you would probably see a much steeper, or shrinkage curve, sorry, here than what we're seeing in this case. Perfect. What we're going to do now is we're going to go back to the PVT table, and we're going to assume that our hydrocarbon pore volume is 10 million reservoir barrels. and we're going to use the formula that I just provided to calculate the oil in place. Okay, so we're going to make that that calculation, all of us, right now. So that will be formation volume factor. That will be, we learned that earlier today, that oil in place, that is the hydrocarbon pore volume divided by the total formation volume factor. And then the gas in place is this is just oil in place multiplied with the GOR. Okay, so those are the formulas. And we know that, okay, if a hydrocarbon pore volume is 10 million barrels, bring that to surface, well, it should shrink because that's what oil likes to do. So if we do the first one, the oil in place is equal to 10 million divided by 1.382. And that gives us 1.382. It gives me 7.2 million barrels. And then I take that number right there and I multiply that with my GOR to get, and my GOR was 750, should be, that is 7.2 STB multiplied with 750 scopes per STB. And that gives us 5.4 BCF. So that's what I'm getting. I think that's what the answer was as well. So the formulas are given in the chat here. If you wanted to export this table from the software, you can do that up to the right here, any third-party tool. And what we're going to do now is the thing that I talked about, which is related to QCing. Let's say you have a DCA of an oil and a gas, and then of course at the end of history, if you have their EURs, you can get their cum GORs. And that's where the simple material balance is really nice. That's just 100% valid material balance. And you can go in here and provide an input of abandonment pressure and a cumulative GOR. That's what I thought we could do here in this case. So if we go all the way down here, it doesn't require any any simulation or anything fancy. Go down to simple material balance, and we input an abandonment pressure of 1,000 and a cumulative GOR of 5,000. Okay. When we click save here, if those things were true, these are the recovery factors that we should be looking at for this case. So when I calculated a 7.2% oil in place, then I know that my EUR in this case for this well should be 7.2 multiplied with 0.088, which gives me 632. So EUR for oil would give me 600,000 barrels ish. This 633,000 barrels in this case. And the only thing I did was to have some simple assumptions here. But you would always have some. So typically, you do this the other way around. We see a lot of our clients are doing this often. To make sure that their material balance is honored, that the recovery factors make sense as you cross different fluid windows and whatnot. Okie doke. So the other thing we're going to do now is we're going to flip to a dry gas well. That's this pheasant well right here. So this to many folks that I'm obviously not from the US, but so I was walking around and I think I did this course or versions of Whitson Plus courses probably 50 times or something last year, and I was calling it as well for the peasant well, and that was just very, very bad. And the kind guy that came up, this is actually a bird, anyways, so sorry about that if I insulted someone before on that front. But when you have a well like this that only has gas data, you can't use any like the GOR methods, etc. So you need to flip down to the dry and wet gas input, which you see here. It will ask you for a specific gravity input. So that's relevant for everybody that's dealing with dry gases. And in this case, we're going to use a specific gravity of 0.6. And what you'll see is you get a phase envelope like this. Why is there no two-phase region? Well, so dry that there's no two-phase envelope, seems like in this case. And you will see that your PVT table will look very different. Your RV term is 0. Doesn't have that like dew point and all that stuff. You'll have a gas viscosity and you have a gas expansion factor right there as well. I'll show that one more time at the top here. You have the pheasant well. You've made sure that your reservoir fluid composition is now the method is changed to dry and wet gas, and then you're using 0.6 as your specific gravity. And then you click save. And you can do the same thing by specifying hydrocarbons. So again here, when you look at your composition, no hydrocarbons there or non-hydrocarbons, and you can input a nitrogen of 0.5, a CO2 of 0.7, and then we leave the hydrocarbon or the H2SS as this. Nobody likes that anyways, or not that I've heard of. And that's the way you get this number right here. Okie doke. Yeah, the PVT table looks a little bit different, as I mentioned, and that's just because it's a dry gas table. And the reason again why, I'll feel very comfortable in a dry gas basin to use the default equation of state, because most of the components that you see here, the nitrogen, etc., they go up to C6 typically, and the components that is making up this reservoir fluid, the properties there are really well known. We know what the properties are. They're well established, and when you're primarily dealing with fluids that have primarily methane and stuff like this, it's much more predictable than if you are dealing with fluids that have a lot of these components that are heavier than C7, etc. Yeah. In terms of there's a few advanced topics in the course that is in the appendix that are very PVT related. For instance, separator oil shrinkage is mentioned there. That is something that can be modeled in the software. See, we have 5 more minutes here, so maybe I can take that for a quick spin just to show you guys an example, separator data example. So that's an example where I would have some kind of PVT data, and I would go in and add some separator data, which is available in the manual. So there's some examples of that. In this case, there's an example of it here. So I'm just going to show that how that looks like for people. So that means that you've measured the rates at separator conditions. That's what you have available. Very, very relevant for flowback data, for instance. So here you see I have oil rate, gas rate, and water rates, and the separator conditions over time. That's what you're looking at there. So in the software, then click upload, and then at the top here, I'm going to just switch to separator rates. And then I can input the time, which will be here, and then I'll just input these guys right here. And there you see I have oil rate, gas rate, water rate, separator conditions over time, and gate pressure. And when I do that, and I click save here, it says the uploaded rates are separator rates and must be converted to stock tank conditions, yada, yada. So that's what's happening behind the scenes now. We're calculating the common process conversion numbers. That's being done. And actually on a daily basis, a separator shrinkage have been estimated on a daily basis with the equation of state. Okay, so it's running this process called common process conversion, and there's more information about that in the appendix slides in the deck that was distributed. It talks about separator oil shrinkage. It also talks about some more advanced topics related to PVT extrapolation. Talks about compositional tracking, what's unique for shale PVT, etc. If you one last thing that I wanted to talk about is where do you actually change reservoir water in the software. So very important that when it comes to reservoir water, you could see that water viscosity typically goes from 0.3 to about 1 centipoints at ambient temperatures, and the compressibility of water is fairly low. And then reservoir brines, they exhibit a very, very slight shrinkage when produced to the surface. And the brine that is sharing pore space with hydrocarbons will always contain limited amounts of gas in solution. But when it comes to the software, if you want to change any of the water properties, in the analysis tab, you have salinity here, but also in numerical RTA, in the numerical model, and the fluid initialization, you can edit the water properties. And if I do that, this is fresh water. But if I added, fresh water, it can go from 0 to maybe 300,000 parts per million. So you see that has a big impact. So you need to have a relationship to what your salinity is in general. So it goes a little bit up to 100,000. Then if I make it 200,000 like this, you see that it's a big difference, especially if you have really, really salt stuff or saline stuff. You're dealing with 2x the water viscosity and a 20%, 25% increasing water density compared to fresh water. And that will have an impact on your bottom pressure calculations. It will have an impact on your numerical model, etc. Good example, if you're modeling, so in Whitson Plus, you can model both bottom pressure calculations for water during an injection process. And now also in the numerical model, you can kind of model these SWD wells. And of course, dairy will be really important because it will change, of course, your bottom pressures a lot in general. So with that, the clock is 12. I don't have a hard stop, but I didn't want to go through more in the course today. Hopefully this has taught you that all the stuff in the software when it comes to PVT is really rigorously thought about and derived. I think there's nothing more rigorous than these equation and state models that is being used. And it's not a black box. Everything here can be accessed and read more about in the software, especially in the manual. Up to the right in the software, you have a question mark, and you can read upon all the different methods, what the assumptions are, etc. So we really appreciate if you have questions, feel free to reach out to us anytime. And also the team has done a really good job of documenting all the different methods and functionality when it comes to the PVT part. So it's not a black box, and it's a lot of things you hopefully have learned in the course today that provide some more rigor and theory related to it. So with that, we'll just stay in touch, and I'll stop the recording here. And if there's anything else, we'll just follow up offline. Thank you a lot.